The thing that scares them for astronomers is the Eridanus Supervoid. This is because it lines up with the CMB cold spot, which is a strange extra cold spot in the glow from the Big Bang. Astronomy says that we almost never see voids that are very deep and run along our line of sight. This means that the light would have to be cooled. Our big picture organisation isn't quite right as shown by maps. We need to explain this. If they don't, new physics or hidden patterns are making the sky cool down. I'm not sure about either answer. People who work in the Eridanus Supervoid can't sleep at night because it's a very tense place for the data trail. What counts as a supervoid? To begin, think of void in the sense of the cosmic web, which is an area of space where the usual mass of matter is less than the cosmic mean. In order to measure that dip, astronomers use a density difference, how far below average it is, and a size, how far the underdensity spreads out in 3 dimensions. Galactic scans usually find gaps that are a few tens of millions of light years across and not very dense. A supervoid, on the other hand, is the big one. It's usually hundreds of millions of light years across, much deeper than normal voids. It lacks more galaxies and mass than normal voids, and it often goes along our line of sight. A long, consistent underdensity can change the way background light looks after crossing it. It's not just a blank spot. 2 details matter most for that last point. First is the density profile, how fast the void falls below average inside and how sharply it climbs back at the edge. Many real voids are compensated, meaning the empty interior is ringed by a slight overdense shell that restores the cosmic balance. Second is time evolution. In our accelerating universe, underdense regions expand faster than average. Their gravitational potential shallows with time, and that evolution can leave a fingerprint on the cosmic microwave background, CMB. When CMB photons pass through such a region, they can emerge slightly cooler than they entered, an imprint known as the late-time integrated Sachs-Wolfe (ISW) effect. The bigger, deeper, and more stretched the void, the stronger the imprint you can hope to detect. Size thresholds are fuzzy because surveys differ in depth and resolution. But a useful rule of thumb is this: if a void is so large and so underdense that it's rare in standard cosmology and plausibly capable of producing a measurable ISW signal on its own, people start calling it a supervoid. A related practical test is tomographic. Slice the sky by distance and ask whether your hole stays empty across many slices or whether you're stacking several modest voids by accident. A true supervoid should look like one long trough in density along a continuous range of distances, not a collage of unrelated dips. How do you measure one? Galaxy redshift surveys are the workhorse, since galaxies trace mass statistically. You count galaxies in a region, correct for survey depth and selection effects, and compare with the cosmic mean. Radio catalogues and quasar counts offer complementary traces that cut to larger distances. Weak gravitational lensing is another key test. Even emptiness bends light, just in the opposite sense of a cluster. So a real supervoid should create a small but coherent anti-lensing signal, a dip in convergence that cross-checks the galaxy counts. Each observable has its own pitfalls. Photometric redshifts blur structures, masks hide galaxies behind the Milky Way, and lensing signals are tiny and noisy. That's why credible supervoid claims combine multiple, independent datasets. The Eridanus Supervoid is proposed because an underdensity in that direction appears to line up with the famous CMB cold spot, an unusually cool patch of the microwave sky. For a void to be the culprit, it would need to be both deep and extended primarily along our viewing direction. Think of a long, low-density tunnel the CMB crossed. Some reconstructions indeed find a long underdense trough through that sky cone. Others see several medium voids rather than one behemoth. The difference isn't academic. A single, very large, very deep structure could in principle punch a colder than usual hole in the CMB. A chain of ordinary voids likely cannot produce enough cooling on its own. If the Eridanus structure is surrounded by a beefy overdense rim, part of the CMB effect cancels, muting the imprint. Conversely, an uncompensated void, where the deficit isn't balanced by a strong shell, should have a bigger net ISW signature. The geometry and compensation together determine whether supervoid is a label or a genuine physical explanation for the cold spot. Discovery timeline from the CMB cold spot to galaxy underdensity maps. We don't start with galaxies in this story, we start with microwaves. In the early 2000s, satellite images of the cosmic microwave background, CMB, showed a strange feature, the cold spot, a big, cooler than usual area in the southern sky near the constellation Eridanus. Wavelet studies showed that its size and depth were not at all consistent with what random CMB changes should produce in a normal universe. Right away, there were two camps. Statistics sometimes roll their eyes. This could be a fluke, said one. The other person said, find a structure in the foreground that is big enough to explain it. Before optical surveys took the stage, radio data offered a tease. Sky maps of radio sources suggested fewer radio-loud galaxies in roughly the cold spot direction, a first hint that the line of sight might be underdense in matter. But radio catalogues are messy. Source populations evolve, flux limits bite, and the galaxy's own emissions complicate counts. The field needed three-dimensional maps. The mid-2000s brought them. All-sky infrared catalogues paired with near-infrared and optical data produced photometric redshift galaxy maps that could be sliced by distance. When astronomers cut a cone through the cold spot and stacked galaxy counts across redshift bins, they saw a trough. Fewer galaxies than average across a very long depth range. The press called it a supervoid because it looked big in both angle and distance, seemingly tailor-made to cool the CMB via the late-time integrated Sachs-Wolfe effect. Then came the hard questions. How deep is the trough once you correct for selection effects? Does it persist when you use spectroscopic redshifts which pin galaxy distances far more precisely? Is it a single coherent underdensity or several moderate voids aligned by chance? Different teams, using different catalogues and methods, reached different emphases. Some reconstructed a long, underdense corridor. Others found that splitting the line of sight into finer bins breaks the one big hole picture into multiple pieces, each too weak to explain the cold spot alone. At the same time, the CMB side put up its own obstacles. Planck's better maps showed that the cold spot was a low-temperature area. They also tightened the general statistics of large-angle anomalies, which pushed the meanings back toward rare but not impossible. Planck's lensing maps added another check. If Eridanus hides a big mass loss, the lensing convergence should weaken in that direction. Any such dip is very small. Some studies said it was just a hint, while others said it was just noise. If there isn't a strong lensing loss, there is less chance of a single, very deep, centrally concentrated supervoid. Large-scale structure surveys piled on more data, deeper imaging, IDA-2RI, dark energy survey fields, wider spectroscopic programs, and improved photometric redshift calibration refined the 3D picture. The underdensity remained as a pattern, but its severity softened and its coherence fractured in some reconstructions. Stacking techniques that average the ISW signal over many voids did recover a void CMB correlation on the sky overall, which says the physics works in aggregate, but that still doesn't prove the cold spot is the poster child of a one-off, supersized case. By the early 2020s, the narrative had stabilized into a tense draw. On one hand, the Eridanus line of sight does look unusually underdense across a long stretch of cosmic time. On the other hand, the reconstructed depth and geometry often fall short of what's needed to explain the full cold spot amplitude without help. Alternative ideas like a statistical fluke or a relic topological defect, a cosmic texture, linger at the margins, kept alive precisely because the just a giant void story hasn't landed a knockout blow. The CMB cold spot. Map first. These are full-sky cosmic microwave background CMB maps from WMAP and Planck. The cold spot is a large, cool area in the southern sky that points toward Eridanus. The CMB is full of many small hot-cold spots, but this one is big, several degrees across, and very deep compared to the random changes you'd expect from a Gaussian, statistically isotropic sky. If you smooth out the map, you can still see a clear dip, and using wavelets set to a few degree scales, like the spherical Mexican hat, to filter it, makes it stand out even more. How cold is cold? The central decrement is tens to over 100 microkelvin below the mean, depending on how you define the aperture and filter. Two profiles matter. The first is the raw temperature map, a bowl-shaped dip with a cool center and a gentle rise outward. The second is the compensated filtered profile from wavelets and needlets that suppress large-scale drifts and highlight localized features. By construction, that can make the cold spot's contrast look starker. Neither trick invents the feature, but your chosen scale and filter change how improbable it appears. If you simulate thousands of lambda CDM CMB skies and look for the single most extreme cold region after you've scanned many filter sizes, locations, and statistics, a look elsewhere aware test. The cold spot's p-value softens to the percent level or a few percent range. If you decide the statistic after seeing the data a posteriori, it can look like a 3 sigma outlier. If you pre-register the test a priori and include the search freedom, it slides closer to 2 sigma-ish. In plainer terms, weird, but maybe not cosmology breaking. This spread in quoted sigma is why papers sometimes sound like they're talking past each other. Non-Gaussianity tests add texture. Wavelet space kurtosis, how heavy the tails are, is higher than expected at cold spot scales, hinting that the distribution of fluctuations there isn't perfectly Gaussian. Minkowski functionals and other morphological stats also flag the region as unusual in shape and topology compared with random skies. But again, once the look elsewhere penalty is folded in, those alarms dim rather than vanish. Polarization is a key tiebreaker. Primary CMB temperature, hot/cold features come with correlated E-mode polarization patterns, while late-time effects like the integrated Sachs-Wolfe ISW imprint from large structures largely do not. Planck's polarization maps don't show a screaming anomaly aligned with the cold spot. They look broadly consistent with lambda CDM expectations. That doesn't kill the void idea. An ISW contribution would be mostly temperature only. But it does lean against explanations that require a radically different primordial origin. Foregrounds and systematics get audited hard. Component separation pipelines, SMICA, NILC, etc., attempt to peel off galactic dust, synchrotron, and extragalactic sources. The cold spot persists across methods and frequencies, which argues against a simple foreground mistake. Beam asymmetries, scanning strategy, and map-making artifacts have also been stress-tested. No single smoking gun emerges. Still, absence of evidence isn't evidence of absence, hence the caution in declaring victory. Now what do we do? You can make up a story where the cold spot is an extreme but not impossible statistical change in a Gaussian field. It's not common enough to be remembered, but it's also not uncommon enough that a big universe could roll it. A line of sight mass shortage, a supervoid, can be seen by another person thanks to the late-time ISW effect, which turns a random dip into a really impressive valley. You can also leave the door open for exotica, like textures, as long as the polarization is right and there aren't any clear fingerprints in the foreground. Even if the cold spot is just a one-time event, it shows us that our gut feelings about things that seem improbable can be wrong after we've looked at the sky through many lenses. If it needs extra help from structure, then that structure, our line of sight to Eridanus, must be unusually deep and long. This checks the tails of the lambda CDM large-scale structure. Building suspense. If new lensing and spectra show that Eridanus isn't deep enough to make this temperature crater, then the oldest light we can see is being chilled by something we haven't modelled correctly. What radio surveys actually show in Eridanus? Before deep optical/IR tomography was fully developed, radio astronomy gave us the first 3D hint. Count the number of faraway radio galaxies that point toward the cold spot and see if the sky seems less empty. The NRAO VLA Sky Survey, NVSS, at 1.4 GHz did most of the work. It mapped most of the sky north of about -40° declination with fine detail and high sensitivity. NVSS sources are mostly active galactic centers and galaxies that are making stars at moderate to high redshift. Because of this, their surface density can be used as a rough indicator of large-scale mass over very large areas. The basic test is deceptively simple. Pick a center near the cold spot, choose an angular radius, apply flux cuts to avoid incompleteness and bright source systematics, mask obvious galactic contamination, and compare the number density of NVSS sources in that aperture to the average at similar declinations. Early analyses reported a deficit, fewer radio sources per square degree than expected, roughly aligned with the cold spot footprint. The direction matched, the angular scale wasn't crazy, and the press nicknamed it a hole in radio galaxies. But NVSS comes with strings attached. Sensitivity and calibration vary slightly with declination and scanning strips. Residual stripes and small flux scale drifts can masquerade as large angle gradients. The galaxy itself complicates counts via diffuse synchrotron emission and source confusion near the plane, hence the need for aggressive masking. Different flux thresholds shift the redshift mix of sources and the balance between AGN and star-forming galaxies, altering how tracer-like the catalogue is. Even the known NVSS diapole and hemispheric asymmetries must be modelled lest they bleed into local deficits. Cross-checks help. Southern surveys like SUMS at 843 MHz and low-frequency maps, EGREU, TGSS at 150 MHz, provide independent looks with different systematics and selection functions. Some studies find qualitatively similar underdensities toward Eridanus under certain cuts. Others see the signal weaken or become sensitive to analysis choices. That inconsistent resilience is a warning. The radio hole hint is interesting, but it isn't a slam dunk. What does a radio deficit actually imply if real? NVSS sources are broadly distributed in redshift, often peaking around Z approximately 1. So a surface density dip suggests an integrated matter underdensity over a long path length, not a tidy single void at a pinpoint distance. That matches the elongated trough supervoid concept, a long, mild to moderate underdensity stacked along the line of sight. However, because NVSS lacks precise redshifts for individual sources, it can't by itself prove coherence in 3D. It can motivate targeted optical/IR follow-ups with photometric or spectroscopic redshifts to map the trough tomographically. Could radio sources themselves bias the CMB temperature? Unresolved radio emitters typically bias CMB maps hotter, positive temperature, not colder, and component separation pipelines aggressively mask bright sources and model the residual background. That makes radio foregrounds made it cold, an unlikely primary explanation. The value of NVSS here is as a tracer. Fewer radios hints at less mass, which could boost a late-time ISW cooling contribution, if the deficit is deep and coherent enough. The lens angle is very important. A real lack of mass should also lower the weak lensing shear and convergence of the CMB from background galaxies. The supervoid story is less strong if radio counts show less stuff, but lensing maps don't show the same thing with at least a small convergence dip. It's not clear yet what the lensing results are for Eridanus, because the signal is weak and the data are noisy. That leaves the radio deficit in a state of uncertainty. It's not clear what will happen. The ISW effect. The cosmic microwave background, CMB, has a cold spot left over from Eridanus. Why would this be? The simple, plain CDM answer is the late-time integrated Sachs-Wolfe ISW effect. Gravitational wells and hills that photons pass through don't stay the same in a universe that is expanding faster. They slowly break down. It is said that a well is shallow when a CMB photon falls into it and climbs out later. This means that the well gives back a little less energy than it took, making the photon a little hotter. For a void, flip the sign around. A photon goes over a possible hill that flattens over time. It loses a little more than it gains and comes out a little cooler. What you're seeing is the ISW effect at late times, mostly at redshifts below about 1. How strong the ISW wave is controlled by 3 things. First, let's look at the gravity potential amplitude. Photons start their trip in deeper wells or higher hills, where the potential difference is bigger. Next, how much does that potential change while the photon is inside? Dark energy must be affecting the crossing at that time. Third, there is shape. The potential has more time to change, while the photon is travelling along a longer path through the object. That's why a long straight-through tunnel gap can work better than a short sphere with the same depth in the middle. Compensation matters. Many voids are surrounded by a gentle overdense rim that compensates the interior mass deficit. That rim creates the opposite temperature sign and partially cancels the void's core signal, often producing a cold center with a faint hot ring in filtered CMB profiles. An uncompensated supervoid, one without a strong rim, would deliver a larger net cooling, but such profiles are rarer and must still fit into the observed large-scale structure. What's stopping them is scale. Individual garden variety voids leave ISW marks that are only a few microkelvin deep, which is much less than the cold spot's depth of tens of microkelvin. A statistical ISW detection that fits with theory has been found by stacking hundreds of voids in surveys like SDSS or DES. This shows that the process works when looked at as a whole. To turn one line of sight into a standout cold depression, you have to turn on a lot of different dials at the same time. These include an unusually large angular size, several degrees, a lot of underdensity, a difference in density that is much lower than the mean, and strong elongation across a wide redshift range where dark energy is already important. In Eridanus, that's the supervoid recipe that people look for. Observationally, the ISW hypothesis is falsifiable. Reconstruct the 3D density field along the cold spot cone with photometric and spectroscopic redshifts. Predict the exact temperature profile that voids of that depth, shape, and redshift distribution should imprint, and compare with the CMB map using match filters. Cross-correlate the same region with CMB lensing convergence. A genuine mass deficit should also mildly depress the convergence field. If the predicted ISW signal falls far short of the observed cold amplitude, even under generous geometry, then a void can't shoulder the blame alone. There are some things to keep in mind. Photometric redshift mistakes blur buildings along the line of sight, making it look like they are longer than they really are. A galaxy's bias, or how it finds its mass, needs to be described in order to turn numbers into potentials. Masking and picking tools can make a hole look real or fake. When looking at the CMB, look elsewhere effects make it harder to figure out how important something is. If we tune our filters after looking at the sky, the cold spot will always look different. So, robust tests use preset statistics, expectations made from the rebuilt LSS, and several traces, such as galaxies, quasars, 21 cm HI, and lensing. What would success look like? A coherent underdensity stretching across hundreds of megaparsecs in co-moving distance, with a modest compensation, peaking at redshifts approximately 0.2 to 0.8 and aligned closely with the cold spot's core, plus a predicted temperature dip that matches the observed profile in both depth and radial shape. What would failure look like? A patchwork of smaller voids whose net ISW sums to only a few microkelvin, a lensing convergence that doesn't dip accordingly, or a reconstructed geometry whose compensated edges create the wrong ring-to-core ratio. Rees-Sciama. The Rees-Sciama RS effect is the nonlinear cousin of the linear ISW. ISW comes from the smooth, linear loss of large-scale potentials in a world that is speeding up. RS, on the other hand, comes from structures growing and rearranging themselves in ways that aren't linear. As clusters break apart and voids grow, their gravitational potentials not only decrease, but also change shape. As photons travel through these changing landscapes, they pick up small extra redshifts or blue shifts. RS is a second-order correction, which means it is slight, but can improve the impression of structures that are very deep or changing quickly. For voids, the sign remains cooling. A photon crosses an expanding underdensity whose potential hill is changing non-linearly. It gives up slightly more energy than it gets back. Intuitively, the faster the void's interior expands relative to the background, and the more uncompensated it is, the larger the RS contribution. The dependence on redshift is two-sided. At higher redshifts, structures are less evolved, smaller RS. But the photon spends more cosmic time inside. At lower redshifts, dark energy accelerates void growth, which can amplify RS, up to the point where overall potential decay, the linear ISW piece, dominates. How big can RS be? State-of-the-art simulations and analytic estimates typically find individual void RS signals at the microkelvin or sub-microkelvin level, smaller than linear ISW for the same structure. That's why RS is usually discussed as a tweak, not a primary driver. However, for unusually deep, elongated and undercompensated voids, RS can steepen the central dip and alter the detailed radial profile, helping to reproduce features like a cold core with a mild hot ring after wavelet filtering. In that sense, RS is less a replacement for ISW than an amplifier for the most extreme geometries. Detecting RS is hard. It has the same frequency spectrum as the primary CMB, purely gravitational, so you can't separate it with a multi-frequency component cleaning the way you do for thermal Sunyaev-Zeldovich effects. It's also coherent on degree scales where primary CMB variance is large, burying RS under cosmic noise. The best shot is targeted, template-based filtering. Reconstruct the 3D density and velocity field of a candidate structure. Forward model its combined ISW plus RS imprint. Then fit that template to the CMB map. Even then, degeneracies with primary fluctuations and uncertainties in the reconstruction can wash out significance. Eridanus is the stress test. If tomographic maps really reveal a long, deep trough with limited compensation, its nonlinear evolution should contribute a small RS boost on top of ISW. Conversely, if the line of sight is a chain of moderate voids separated by walls, their nonlinear pieces won't add coherently, and RS stays negligible. Weak lensing shear and CMB lensing convergence help here. RS-relevant voids must also show a corresponding mass deficit and outflow pattern. Without those, invoking RS becomes special pleading. You should not mix up RS with the Kinetic Sunyaev-Zeldovich KSZ effect that happens when electrons move in large-scale flows. KSZ can also make temperature spikes on a degree scale, but it depends on baryon distribution and speeds in a different way, and it tends to be small and sign mixed in void directions. Second, let's say that RS can suddenly provide tens of microkelvin all by itself. Even the most hopeful models can't get above a few microkelvin per structure. To say more, you'd need either strange void physics or starting conditions that aren't in the same family. So what does that mean for the Terrifies astronomers angle? RS reminds us that our conclusion depends on correctly figuring out complex growth. If the carefully reconstructed Eridanus trough plus RS still can't get close to the observed cold spot depth, then the nonlinear universe is ruled out. The focus then returns to alignments by chance or non-standard origins, textures, early time imprints that are limited by polarization and other large-angle anomalies. If, on the other hand, an accurately measured, undercompensated extended void plus RS and ISWU together duplicate the cold spot's amplitude and profile, then lambda CDM can still work, but only if it allows a void that is so extreme that it lives in the very tail of cosmic statistics. One monster or many? Point a cone at the cold spot and ask straight out, is there one continuous unified underdensity that spans a huge moving depth, or are we just stacking a bunch of normal voids that happen to line up? Line of sight tomography is the only way to find out. It reconstructs the three-dimensional density field in a series of redshift shells and checks to see if the loss stays as a single dip. It all begins with galaxy catalogues and their redshifts, which tell us how far away each galaxy is. Photometric redshifts estimate distance from a galaxy's colour, but they come with uncertainties of about delta Z equals 0.02 to 0.05. These small errors can blur structures along the line of sight, making several smaller voids appear as one long, stretched out sausage shape. In contrast, spectroscopic redshifts with precision around delta Z equals 10 to the power of -4 are far more accurate, though they're slower and more expensive to collect over wide regions. To get a trustworthy result, scientists need both broad photometric surveys to locate large-scale gaps and focus spectroscopic data to refine the exact shapes and boundaries. Next comes the reconstruction step. Most void-finding algorithms, such as the ZOBOV or VIDE watershed methods, spherical underdensity scans, and density threshold techniques, start with a map of galaxies, correct for observational biases, and then locate areas that fall below the average density. In tomographic analysis, this process is repeated across slices of redshift, and the resulting voids are then linked together across time. If a genuine supervoid exists, it should appear as a connected chain of overlapping low-density regions, forming a continuous spine through redshift. The density profile should change smoothly with redshift, and any compensating ridge, a denser boundary around the void, should trace a single, coherent structure rather than a scattered patchwork of unrelated clumps. As important as depth is geometry. When you cut an angular map, what looks like one big hole can turn into several middle voids that are grouped like beads. On the other hand, a real line-of-sight tunnel may not look very big in one slice, but it can connect to a strong dip in many bins. That's why simple, single-bin plans are wrong. Strong pipelines describe ahead of time the survey's photo Z errors, masks, and completeness, and then they deconvolve those effects to get an idea of the real three-dimensional difference. Bayesian reconstructions, like log-normal priors and Hamiltonian sampling, can help by making things physically smooth without getting rid of real traits. The decision is based on two checks for reason. First, there is continuity. Plot the best fit density minimum along the cone versus the distance that the points move together. If it shakes all over the place, you probably have a stack. If it follows a smooth path, you might have a tunnel. Second, there is compensation. Find the average density in shells that are moving in a circle. There may be a void ridge pattern that can be seen in a single supervoid that changes slowly with redshift. A stack tends to restart this pattern in each slice. When you add in strange speeds caused by redshift space warping, you get an extra hint. Flows that are coherently away from the center should line up with a real, long-lasting underdensity. Pitfalls are legion. Photo Z outliers can plant fake emptiness or fill real dips. Stellar contamination near the galactic plane reduces apparent counts. Galaxy bias evolves with redshift. If you do not calibrate how traces populate halos as a function of Z and luminosity, your mass trough is just a galaxy trough. Mask edges mimic void rims. Aggressive apodization and in-painting control that, but at the cost of signal to noise. Finally, a priori choices, bin width, void merging criteria, minimum contrast, can swing you from one to many, unless you lock them before peaking. Why does this split matter? Because the predicted CMB imprint is sensitive to coherence. A single, long, undercompensated trough can accumulate a larger late-time integrated Sachs-Wolfe contribution than a chain of compensated medium voids whose positive rims partially cancel neighbours. Likewise, the Rees-Sciama tweak adds coherently only if the interior evolves as one structure. Lensing 2 expects a smoother, broader convergence dip for a tunnel and a bumpy, lower amplitude pattern for a stack. Void weak lensing. Even empty space can bend light. Compared to the average universe, a cosmic void has less mass, which causes light rays passing through it to spread out slightly. This effect is called negative convergence, written as kappa, less than 0, and it creates a subtle tangential shear pattern, a gentle stretching of background galaxies around the void center. For a truly large supervoid, this anti-lensing signal should be consistent over several degrees of sky. The distortion on each galaxy is tiny, but by stacking data from millions of them, astronomers can detect the pattern statistically. If the Eridanus region is really lacking in matter, weak lensing should reveal it quietly, even if galaxy counts already suggest it loudly. So what should the signal look like? In an ideal spherical void, the convergence profile dips below 0 inside the void, then rises back towards 0, or even slightly above it if there's a dense ridge surrounding the edge. The related tangential shear, written as gamma sub t, is negative near the void's core and crosses 0 around the ridge's boundary. The strength of both effects is extremely small. The absolute values of kappa and gamma are typically between 10 to the power of -3 and 10 to the power of -1 to the power of -4, reaching a few times 10 to the power of -3 for exceptionally deep, nearby voids. That's far below the random shape noise from galaxies' natural ellipticity, which is about 0.3 per component. So researchers must average over enormous galaxy samples and apply strict controls to minimize measurement errors. There are two lensing avenues here. The first is galaxy-weak lensing. Measure shapes of distant galaxies behind the Eridanus cone, bin them by photometric redshift to keep them behind the void, and stack the shear tangentially around the reconstructed void center S. You must model the redshift distribution of sources, AN of Z, weights, and intrinsic alignments. Apply stringent point spread function corrections, and test for B modes, a null channel that should vanish if systematics are tame. The second is CMB lensing, reconstruct kappa from CMB temperature/polarization maps, and read off the convergence toward Eridanus. Galaxy lensing offers higher resolution but smaller area and lower redshift leverage. CMB lensing sees the entire integrated mass to the last scattering surface, with coarser resolution but clean source redshift. A supervoid verdict needs consistency across both. If galaxy counts say deep trough, galaxy shear should show a matching negative gamma T with a radial scale aligned to the void's compensation radius. CMBK should show a broad degree scale dip. Disagreement does not automatically kill the void. Galaxy bias and tracer selections complicate counts, but a flat lensing profile forces any underdensity to be shallower or more compensated than advertised. Conversely, a significant lensing dip with only a modest galaxy deficit would hint at bias evolution or at missing faint traces. Analysis choices are decisive, centering on the correct void position, especially for a lumpy, stacked structure, can make or break the signal. Miscentering smears gamma T towards zero. Including foreground galaxies as background dilutes the measured shear. Overly aggressive masking around bright stars and the galactic plane changes the effective survey window and can bias profile estimates unless forward modelled. And because we are testing a single direction, not stacking thousands of voids, jackknife and simulation-based covariances are required to get honest error bars. What numbers would be convincing? A negative gamma T detection at greater than or equal to 3 sigma over a wide annulus, say 0.5 to 5 degrees, a profile consistent with the independently reconstructed density, including any compensating ridge, and a matching degree scale CMB kappa dip in the same coordinates. Add a null B mode, stable results under reasonable centering and weighting changes, and cross-checks with randomized cones to rule out survey edge artifacts. Put that together, and the mass deficit is real claim becomes robust. Photometric versus spectroscopic redshifts. Redshift is the backbone of any Eridanus map, and the choice between photometric and spectroscopic distances can make a supervoid appear or vanish. Photometric redshifts come from galaxy colors in broad filters. They're fast and deep, but imprecise, with delta Z about 0.02 to 0.05. That blur smears structures over hundreds of megaparsecs and stretches anything along our line of sight, exactly the geometry that can mimic a stronger ISW signal, so multiple ordinary voids can inflate into one sausage-shaped tunnel. Spectroscopic redshifts, by contrast, use discrete spectral lines and pin galaxies to delta Z about 10 to the -4, cleanly resolving walls, filaments, and true void interiors to reveal whether a tomographic trough is continuous or just a chance stack of dips. The trade-off is coverage. Spec-Z maps are shallower or sparser across the full Eridanus cone. The credible strategy is to mix both. Use wide, deep photo Z to find candidates, then targeted Spec-Z to lock the spine. 3 photo Z pitfalls loom large. First, catastrophic outliers. A small fraction of galaxies get wildly wrong distances, populating redshift slices where they do not belong and faking or filling apparent emptiness. Second, redshift-dependent selection. Magnitude limits and color cuts shift the tracer population with Z, changing effective bias and completeness. If you do not forward model those effects, a mass trough may be a tracer trough. Third, extinction and stellar contamination. Galactic dust reddens galaxies and steals faint ones. Misclassified stars dilute counts. Both vary across the sky and can carve artificial deficits in the exact direction you are trying to study. Mitigations exist. Clustering redshift techniques cross-correlate photo Z samples with Spec-Z calibrators to recover the true N of Z behind each tomographic bin. Machine learning photo Z estimators trained on representative spectroscopy reduce scatter and flag likely outliers. Adding near IR bands tightens constraints. Star-galaxy separation models train per field, plus extinction corrections tied to high-resolution dust maps, suppress large-scale gradients. Critically, all these steps must be folded into forward simulations of the survey's mask, depth, and seeing so, the same pipeline that measures Eridanus also recovers truth in mocks. On the SPEC-Z side, the trap is representativeness. Multi-object spectroscopy often targets brighter or emission-line galaxies, not a fair census of the mass field. You must either weight the sample to match the photometric selection or model the bias evolution explicitly when turning galaxy deficits into matter deficits. Redshift space distortions add more nuance. Outflows from a real void produce coherent velocity signatures that can verify the underdensity. But fingers of God from nearby groups can muddy profiles if not handled carefully. The best test procedure is organised and known ahead of time. Set the cone's tomographic binning and void linking rules before you look, and use SPEC-Z to lock the photo-Z correction from outside the cone. Come up with a three-dimensional density field that includes photo-Z scatter uncertainty transmission and bias evolution. Then add focused SPEC-Z along the candidate spine to check for continuity. Does a single density minimum move through successive slices, or do different dips blink on and off? First, turn the best fit density profile into a gravity potential. Next, guess the ISW plus RS temperature profile and the weak lensing convergence kappa. Finally, compare the guesses to the data using filters that match. Diagnostics should match up. A real long void has I, a smooth, undercompensated density trough in photo-Z maps. I-28, a coherent SPEC-Z skeleton with persistent minima. I-28, a mild, degree-scale negative kappa in CMB lensing and galaxy shear. And IV, a temperature dip whose depth and radial shape match the forward model within errors. If any part breaks, like SPEC-Z breaking the spine into beads or lensing staying flat, the case for a single supervoid gets much weaker. Foregrounds and systematics checks. On both the galaxy mapping and CMB sides, you have to rule out everything that could be a fake supervoid before you can call it a supervoid. Start with scans using light and infrared. Galactic dust makes galaxies look less bright and red, which changes the photo-Z and lowers the surface densities. Star contamination changes with latitude and can lower counts. Seeing, skylight and changes in air mass change the depth across the area. Unless you fix them with per-exposure depth maps, star density templates, and high-resolution extinction maps, each effect leaves behind degree-scale slopes that are the same size as the cold spot. After making the changes, you still need to forward model these fields into fake catalogues and show that your gap finder doesn't choose masked or shallow areas more often than others. Survey masks and edges are repeat offenders. If the Eridanus cone grazes bright star masks or low exposure zones, annular counts can pick up artificial rims that look like compensation walls. The fix is aggressive apodization, soft mask edges, in-painting to fill holes in maps used for filtering, and null tests with rotated or randomized cones that sample identical mask complexity away from Eridanus. A robust underdensity should survive those rotations. NVSS exhibits declination-dependent striping, small flux-scale drifts, and a known large-scale dipole. Flux thresholds chosen to avoid incompleteness also change the redshift mix. Cross-checking with independent surveys, e.g. SUMSS, TGSS, and repeating the analysis under multiple flux cuts and masks are mandatory. A hole that only appears for one catalogue or one flux range is likely systematic. On the CMB side, component separation is the first gauntlet. Galactic dust and synchrotron, free emission, the cosmic infrared background, and unresolved radio sources each have distinct frequency scalings. Modern pipelines, e.g. SMICA/NILC style methods, combine channels to isolate the CMB, but residuals remain at low levels. A real cold spot should appear with similar morphology in multiple cleaned maps and stay put under reasonable changes in foreground priors. Frequency differencing can sanity check that the spot is achromatic, as a purely gravitational signal should be. Making maps and beams are important. Large-scale noise can be turned into degree-scale features using asymmetric beams and scanning techniques. The biggest modes are messed up by 1/f noise, filtering of time-ordered data, and blocking during spherical harmonic transforms. Teams test these with full pipeline models that run known clouds through it. Any study of the cold spot must show that an Eridanus-like dip is not a normal feature of that system. Also, the wavelet/needlet filter, the angle used for compensated temperature data, and the apodization of the CMB mask can change the quoted significances. These choices can't be changed after the fact if these choices are registered ahead of time. Cross-domain consistency is the ultimate check. If galaxy maps say underdense, lensing convergence should dip slightly. If lensing is flat, then either the underdensity is shallow, undercompensated, or the counts were biased by systematics. If the CMB cold spot's temperature profile is claimed to be void-induced, the predicted ISW ring and core pattern from the reconstructed density must match, not just the overall depth. Jackknife resampling, random cone control samples, and hemisphere flips quantify how often similar deficits appear by chance in equally messy regions. A strong Eridanus study lists all the templates that were used: dust, stars, depth, seeing, shows how they are related to galaxy density, and shows that the underdensity signal stays after each field is taken into account for its error. On the CMB side, it takes readings over at least 2 different maps for each component, and says that the results are stable even when the mask or beam changes. Anything less than that leaves the door open for a smart backdrop to pretend to be a strange thing in the universe. 3D galaxy redshift mapping. An scientist builds a 3-dimensional map of galaxies and asks a simple but hard question: is the number of galaxies and their assumed mass below the cosmic average over a long depth? Wide catalogues are the building blocks. 2MASS is used to find close, bright infrared galaxies. WISE is used to find mid-IR galaxies that are farther away. SDSS and DES are used for deep optical imaging, and newer spectroscopic tools are used to set distances. To begin, a clean cone is drawn toward the cold spot, and tight masks are put on dust, stars, depth, and seeing. Next, volume-limited samples are made to keep the tracer population as regular as possible, with distance. Distances are very important. Photometric redshifts, which are based on colours, cover a lot of ground quickly, but blur structures along the line of sight. Spectroscopic redshifts, which are based on spectral lines, are more accurate but have fewer points of interest. Photo-Z tomography is used to find possible valleys in successive redshift shells, and focus spec-Z is used to sharpen edges, separate blended features, and measure redshift space distortions, peculiar velocities, that show orderly streams from a real void. Selection functions are forward-modelled throughout. The chance that a galaxy will be added to the list relies on its position in the sky, its flux, its colour, and the conditions under which it was observed. The only way to say that an apparent underdensity is cosmological and not instrumental is to simulate those materials and run them through the same process. With a 3D catalogue in hand, teams reconstruct the density field. Methods range from simple counts in cells, comparing each voxel to the mean, to watershed void finders, Zobov/ViDE, and Bayesian log-normal reconstructions that impose physical smoothness while retaining sharp features. Two profiles matter: the radial density contrast delta of R along the cone. Is it one long trough or several dips? And there an overdense ridge that cancels part of the void signal. Because galaxies are biased traces of mass, delta gal must be converted to delta mass with a redshift and luminosity-dependent bias model. Cross-checks with weak lensing help anchor that conversion. Galactic extinction gradients, stellar contamination, and depth variations all sit on degree scales, the very scales of interest. Analysts therefore regress galaxy density against those nuisance maps, propagate uncertainties, and repeat the reconstruction after aggressively down-weighting contaminated regions. Rotated control cones that traverse masks with similar complexity elsewhere on the sky quantify how often comparable troughs appear by chance in survey systematics rather than in matter. What would a convincing Eridanus Supervoid look like in this framework? First, continuity, a persistent density minimum that marches smoothly through consecutive redshift shells across several hundred megaparsecs, not a hopscotch of isolated voidlets. Second, modest compensation, a weak or distant ridge, so the net potential hill remains large enough to imprint a temperature dip via ISW. Third, multi-tracer agreement, similar troughs from different galaxy selections, e.g. blue star forming and red quiescent, after accounting for their distinct biases. Fourth, lensing consistency, a matching degree scale negative convergence profile in CMB kappa or galaxy shear. Failure modes can also teach us something. The expected ISW signal falls apart if spectroscopy breaks up the dip. The void's net gravity trace goes away if the compensation ridge is strong and close. If different traces don't agree after careful modelling of bias, it's likely that selection effects are at play. No matter what the counts say, the mass loss can't be both deep and long if lensing won't show a dip. Quasar and AGN counts. Unlike regular galaxies, quasars, and active galactic nuclei, AGN look into a different part of the universe. They are very bright, can be seen at very high redshifts, and can be picked out by their unique colours, changes in brightness, or radio or X-ray emissions. They can be checked for large-scale underdensity over a long path length by counting them toward Eridanus. The main part of the experiment is the same as the radio galaxy test. You set a cone, pick uniform flux and colour cuts, hide trouble spots in the galaxy, and compare the surface densities to control fields that are the same size. But AGN brings their own selection physics, which brings new risks and strengths. Different AGN catalogues see different kinds of objects, so any surface density dip has to be read through that lens. Mid-infrared cuts, like the WI to W2 AGN wedge, efficiently find dusty, accreting nuclei with only modest contamination. Optical colour boxes, like SDSS, are great for unobscured blue quasars but often misredden ones. X-ray lists, e.g. EROSITA, care less about dust but are shallower over the whole sky. Radio-loud AGN from NVSS or TGSS trace massive hosts and large-scale environments differently than radio-quiet quasars. Each channel has its own redshift distribution, say N of Z, and clustering bias B of Z. So if you see a deficit in radio-loud AGN, it may mean fewer massive halos. If X-ray counts look flat while mid-IR drops, selection colours, not mass, could be the culprit. Because flux limits make steep luminosity functions, small changes in how full the sky is with respect to position can cause big count swings that can look like cosmology. So, analysts make maps of spatial wholeness that show the effective area as a function of flux, colour, and the local background, such as cirrus uncertainty and moon contamination. variability choices need a rhythm. Breaks or yearly windows create stripes that have nothing to do with the structure. As you get closer to the plane of the galaxy, the split between stars and quarks breaks down. Brown dwarfs or compact galaxies can leak into color boxes if machine learning models are not trained per field with spectroscopic truth. Despite those hurdles, AGN are powerful underdensity tracers because they integrate over enormous volumes. A bona fide mass trough stretching across several redshift bins should modestly depress AGN counts in multiple, independent selections once all completeness corrections are applied. Better yet, spectroscopic quasar samples provide precise redshifts, enabling tomographic counts and cross-correlations with galaxy maps to test whether both traces trace the same trough. Because quasar bias is high, they live in overdense halos on average. Converting a quasar deficit into a mass deficit requires careful modelling. Yet that same high bias boosts signal-to-noise for detecting large-scale modulations. Cross-wavelength consistency is the lie detector. If mid-IR selected AGN, optical quasars with spec Z, and radio-loud AGN all show a coherent, scale-match deficit toward Eridanus after uniform masking and completeness corrections, the odds tilt toward a real integrated underdensity. If instead only one channel dips and only under specific cuts, systematics are the prime suspect. Adding X-ray AGN helps. Their different selection and sky systematics make them an excellent referee. AGN allows for two cross-checks of gravity. To begin, there is magnification bias. Lensing by large-scale structure makes sources near flux limits brighter or darker, which changes the counts that are seen. A real mass shortage should make background AGN a little less bright, which would lower counts more than what geometry alone would predict. If you can keep completeness under control, measuring that little bit of extra reduction supports the mass deficit theory. Next, we'll look at cross-correlation with CMB temperature. An ISW signal from the same structures that house AGN should cause a weak, large-scale link between the places of AGN and the temperature of the CMB. Finding the right sign association along the Eridanus cone makes the direct link stronger. Extreme value statistics. How terrifying are the numbers for Eridanus? Extreme value statistics, EVS, ask the same question. Given lambda CDM with certain omega m, pi 8 and dark energy parameters, how often should we see an underdensity along the survey area that is as big, long and consistent as the one pointed toward the cold spot? To get the right answer, we need to look at the tail of a linked random field instead of a bag of random draws. And we need to take into account the choices we made while looking, the look elsewhere effect. First, define a void statistic before looking. Examples: I, the minimum of the smooth 3D matter contrast delta integrated along a fixed cone, a trough integral. The deepest matched filter amplitude for a compensated void template scanned over angle and redshift. The maximum temperature decrement of the predicted ISW plus RS template derived from the reconstructed density, compared to a null lambda CDM sky. Each choice encodes assumptions about geometry, compensation, and redshift range. Pick one and lock it. Next, calibrate the tail by simulation, not analytic wishes. Generate thousands of light cones from n-body or fast approximate simulations. Log normal /Pinocchio /2LPT. Paint galaxies with a bias model matched to each tracer. Impose the real survey mask, depth, and photometric redshift errors. Then run the identical void finding and filtering pipeline you used on the data. Record the extremum of the chosen statistic per Mach, e.g. the most negative trough integral anywhere on the sky outside the galactic mask. The empirical distribution of those extrema gives a prior predictive p-value for Eridanus. The cosmic web has long-range correlations, and your sliding apertures overlap heavily. The effective number of trials, n-F, is far smaller than the number of tested cones or filter scales. Simulations automatically fold that in. Analytic EVS using Gumbel/Weibull forms can be misleading unless you correctly compute n sub EFF from the field's covariance and mask. With a posteriori decisions, the importance is inflated. This is called a look elsewhere tax. It was paid if you centered the cone after seeing the cold spot in the CMB, change the angular radius until the dip looked the biggest, or tune the template to match a hint in galaxy counts. The fair solution is to build that flexibility into the mocks. In each test, have the pipeline look at the same range of radii, redshifts, and centering strategies. Then find out how often the biggest visible difference is greater than the value of the data. You should report that p-value instead of the one you would have gotten if the test had been registered ahead of time. Cosmology matters by design. How many deep troughs you expect depends on sigma 8, the fluctuation amplitude, omega m, matter density shaping growth and geometry, and late time acceleration that drives the ISW effect. The right way to test this is to rerun your mocks across a grid of cosmologies, or reweight them with response functions, and watch how the tail of deepest troughs shifts. If Eridanus looks uncomfortably rare under the Planck best fit, but becomes ordinary with a slightly higher sigma 8, that's a quantified tension you can check against independent probes like weak lensing, clusters, and BAO. If it's rare across all reasonable cosmologies, the anomaly is more robust. Also, don't double count evidence. If you judge rarity once from the galaxy field and again from the CMB temperature, you must model their correlation, because a deep trough should weakly align with a temperature dip via ISW. Treating them as independent unfairly multiplies p-values. A principled test builds the joint distribution, read P of S sub LSS and S sub CMB given lambda C dm, using mocks that include both large-scale structure and CMB realizations, or a CMB map lensed by the same mass. Then simply ask where the observed pair lands in that joint tail. Tails get wider when there are doubts about tracer bias and photo-Z scatter. Change the galaxy bias BZ, the way brightness changes with time, and the catastrophic outlier rates in the mocks using priors from outside measurements. Run the process again. It's not a void if its significance goes away when those nuisances are spread. It's a void that stays extreme when acceptable nuisance draws happen. Primordial non-Gaussianity. If the early universe's density field wasn't perfectly Gaussian, the extreme ends of the distribution, where rare structures like huge voids or clusters live, could be thicker than what lambda CDM predicts. This idea is called primordial non-Gaussianity, or PNG, usually described by the parameter f sub nl. In the simplest local model, the primordial potential, written as phi equals phi plus f sub nl times phi squared minus the average of phi squared, adds a small nonlinear correction to the initial Gaussian field phi. When f sub nl is positive, it increases large-scale power by creating a scale-dependent bias in how tracers like galaxies or quasars cluster. When it's negative, it slightly suppresses that power. Other variants, called equilateral and orthogonal shapes, affect smaller scales differently, but the main point stays the same. Non-Gaussianity changes how often extreme overdensities and underdensities form, and how strongly they influence the CMB through the ISW effect. Could this help explain an Eridanus-sized supervoid? Possibly in two ways. First is the abundance effect. A non-zero f sub nl alters how likely long, coherent underdensities are to appear. Second is the bias effect. On very large scales, the way galaxies trace mass gains ak to the power of -2 enhancement in the local model, which can make galaxy counts show a deeper deficit than the actual matter field. In short, primordial non-Gaussianity could either make a normal mass trough look unusually empty and traceless, or slightly raise the odds of a genuinely extreme cosmic void. Constraints bite hard though. Planck's temperature and polarization by spectra, plus large-scale structure LSS clustering, pin local FNL near zero with single-digit uncertainties. Within that narrow window, the boost to extreme void odds is modest, and the scale-dependent bias, while measurable statistically across huge samples, is too small to transform a stack of middling voids into a single monster along one line of sight. Equilateral and orthogonal PNG are similarly constrained and mostly affect smaller scales than the multi-degree cold spot. Still, PNG is testable here in targeted ways. If Eridanus were riding a positive FNL modulation, you'd expect an enhanced large-scale bias in multiple independent traces, blue and red galaxies, radio AGN, quasars, specifically toward the cold spot direction. Tonnerre, a low L excess in the galaxy CM-BISW cross-correlation amplitude in that patch relative to random patches. And unnitiae, consistency with full sky by spectrum-derived FNL, once the a posteriori selection, we looked because of the cold spot, is paid for. Conversely, if tracer counts look unusually depressed, but weak lensing convergence kappa does not, PNG-induced bias could be a suspect, yet it would also have to show up as a dipolar or low L anomaly across adjacent sky, not just one cone. Void statistics add another angle. The skewness and kurtosis of counts in cells, the topology from Minkowski functionals, and the void size function are mildly PNG sensitive. A single direction won't constrain FNL, but the same pipeline that reconstructs Eridanus should recover these global statistics. If they come out consistent with Gaussian initial conditions, while Eridanus alone looks extreme, PNG is an unlikely scapegoat. Other CMB anomalies. The cold spot isn't alone. Since WMAP and later Planck, astronomers have logged several large angle oddities, low quadrupole power, L equals 2, and its strange alignment with the octopole, L equals 3, nicknamed the axis of evil, a hemispherical power asymmetry where one half of the sky has slightly more variance than the other. Parity asymmetry between odd and even multipoles. A lack of correlation above about 60 degrees in the two-point function, and hints of dipolar modulation. Each one, taken by itself and after look elsewhere penalties, is only mildly significant, but together they make the largest angular scales look a bit too interesting. Where does the cold spot fit? It's one of the most visually striking single features because wavelet filtering pulls it out as a coherent, degree-scale temperature dip with a clear center. By contrast, the axis of evil and the hemispherical asymmetry are global, low L properties, more sensitive to masks and map-making choices. There is some crosstalk though. If you remove best-fit dipolar modulations or reproject along the low L alignment axes, the cold spot's nominal significance shifts a little. That interdependence complicates both skepticism, it's all one low L fluke, and enthusiasm, it's a distinct structure with its own cause. There is extra weight on two checks. Polarization. Main features of the CMB's temperature should be accompanied by corresponding E-mode patterns. Many large angle anomalies, such as parts of the cold spot, don't look as unusual in polarization maps, which leads to ideas of late-time or statistical origins rather than strange primordial ones. Frequency stability, real gravity features are achromatic. The oddities stay the same across cleaned maps put together from very different frequency mixes. This is why simple foregrounds are not enough, but small residuals can still affect low L estimators. There is a wide range of model tries, from the traditional to the fancy. Conservative, everything is lambda CDM, and the outliers are just pairings of chance made stronger by decisions made after the fact, and our limited view of one sky. Baroque. Add things like Bianchi templates for anisotropic expansion, spatial curvature gradients, or leftover topological flaws, textures. Most unusual models can't work because of other limitations like polarization, lensing, or small-scale spectra, or they need to be fine-tuned, which adds another puzzle to the mix. For Eridanus, the anomaly ecosystem sets priors. If multiple large-angle oddities share a preferred axis near the ecliptic or galactic frames, systematic origins, scan strategy, residual foregrounds get a boost. If the cold spot's imprint lines up instead with a specific LSS structure that also dense lensing kappa, a physical, localized cause is more plausible. Targeted cross-correlations help. Do reconstructed void templates correlate with temperature precisely where predicted, while randomized, equally masked directions do not? Do low-L cleaned maps that minimize hemispherical asymmetry still retain a cold spot-like depression? Independence gives you power in the future. Large-scale CMB polarization, better systematics, CMB lensing maps with less noise, and LSS studies, Rubin, LSST, Euclid, SphereX, and SKA predecessors, can all put more emphasis on each oddity from various points of view. It is very important to use a matched filter test with the measured Eridanus density field instead of a standard void template to check if the cold spot's shape matches what gravity says it should be. If the answer is yes, the cold spot is just the visible end of an extreme but allowed density tail. If the answer is no, it goes back into the larger set of anomalies where statistics and systematics fight. Hemispherical asymmetry and axis. Two of the most debated large-angle oddities in the CMB are the hemispherical power asymmetry and the low-L alignment nicknamed the axis of evil. The first means that one half of the sky shows slightly more temperature variance than the other on very large scales. The second notes that the quadrupole, L equals 2, and octupole, L equals 3, appear unusually aligned along a common axis. Both signals live exactly where data processing is hardest. Sky masks, scan patterns, and foreground cleaning all matter most at low L, so they may be real hints of new physics or artifacts. Either way, they demand extra caution. How could these matter for Eridanus? If the cold spot's line of sight sits within the low power or high power hemisphere defined by the best fit dipolar modulation, its significance can shift. An already cold region looks a bit colder in a sky that is globally lopsided. Similarly, if the best fit alignment axis passes near the cold spot, reprojecting the sky along that axis can slightly boost or reduce local contrast, altering wavelet-based anomaly metrics by enough to change a quoted sigma. In short, global large-angle quirks can nudge local anomalies. It's not clear how to understand the imbalance. A real cosmic dipolar modulation would show up in all clean CMB channels, including temperature and polarization, and should be linked to large-scale structure LSS traces through the ISW effect. Once there was a system connected to the ecliptic, scan strategy, or the galactic plane, foregrounds, it would go away as maps and masks got better. Planck error studies show that the imbalance stays at a low but not negligible level in temperature, but its support in polarization is weaker. Its chosen axis is not clearly the cold spot's exact direction, but the neighborhoods overlap enough that crosstalk is possible. It's harder to figure out what the axis of evil is, because alignments depend on sky cuts and estimator definitions, and polarization still won't give a clear support. What tests decide whether these global effects inflate the cold spot? First, rerun cold spot statistics on CMB realizations conditioned to have the observed hemispherical asymmetry and low L alignments. Ask how often cold spot-like dips appear then, compared with fully isotropic mocks. If the conditional frequency jumps, the cold spot is partly riding a global oddity. Second, Rotate the Eridanus cone over many sky positions that share identical mass complexity and lie at the same angular distance from the asymmetry/axis. Compare the distribution of wavelet amplitudes. If Eridanus is unremarkable within that restricted ensemble, the local anomaly is a projection of the global one. On the LSS side, you can search for a matching hemispherical asymmetry in tracer maps galaxies, radio AGN, at the redshifts that drive the late-time ISW. A cosmological modulation should leak into those counts. A purely instrumental CMB artifact should not. Likewise, CMB lensing convergence kappa, derived independently from small-scale CMB fluctuations, serves as a high-pass gravity check. Any true large-scale mass gradient should leave at least a whisper in kappa on degree scales. CMB-LSS cross-correlation tests. The clean way to test whether a supervoid cools the CMB through the late-time ISW effect is to cross-correlate large-scale structure maps with CMB temperature and see if overdensities are a bit hotter and underdensities a bit colder. Globally, you measure the angular cross-power spectrum, say CL of TG, where T is temperature and G is a tracer map like galaxies, quasars, or radio AGN, or the real space correlation W/TG of theta. Many surveys find a low significance but consistent positive ISW signal in aggregate, which confirms the mechanism exists. The sharper Eridanus question is, does the specific underdensity reconstructed along the cold spot cone predict a temperature profile that matches what we observe? The workflow is surgical. First, reconstruct the three-dimensional density field. Call it delta of sky position and redshift, inside the Eridanus cone using photometric redshift tomography anchored by spectroscopy. Convert delta to a gravitational potential phi and its time derivative phi dot under lambda CDM. Then build a forward model for the expected ISW temperature shift, delta TISW of sky position, including a small nonlinear Rees-Sciama term if the void interior is very deep. Second, design a matched filter tuned to that exact template, not a generic compensated top hat, and apply it to multiple component-separated CMB maps to measure the template amplitude, A. Third, estimate significance by rotating the template to many random sky positions that have masks of similar complexity and repeating the measurement. This constructs the correct null distribution with the same filtering choices and look elsewhere freedom. Run parallel checks. Replace the true density with randomized maps that preserve the tracer power spectrum to ensure you're not fitting noise. Use adjacent control cones to verify locality. Repeat the matched filter test with CMB lensing kappa as the CMB field. A true mass deficit should project as negative kappa with the same geometry, though at lower signal to noise. Finally, compute CL of TG or WTG of theta restricted to the Eridanus patch and its immediate surrounds to see whether local ISW coupling is enhanced relative to typical sky areas. You can fake or hide a signal with these two modelling mistakes. First, galaxy bias BZ. To turn tracer counts into mass, you need a bias model. If BZ is wrong, the expected ISW amplitude is off by the same amount that you got the bias model wrong. To set BZ within the cone, use cross-correlations with CMB lensing and external clustering. Second, photo Z scatter. Spreading along the line of sight makes it look like the distance is longer than it really is. And it can also make redshifts look better where dark energy works best, which falsely increases the expected ISW. Use clustering redshift methods and spectral subsamples to calibrate N of Z. Then add that error to the template. To make the void case stick, you'd want a matched filter amplitude close to 1, say A equals 1 within errors, for the Eridanus template across multiple CMB maps, plus stability when you tweak the template, binning, compensation. and a weak but consistent negative kappa signal from CMB lensing with the same geometry. If you also see a mild boost in the local cross power, CL of TG, at low EL compared with control patches, the late-time gravity picture holds together. The opposite outcome, a near zero or with the wrong sign, and kappa not responding while galaxy counts still insist on a deep trough, means that line of sight isn't doing the thermal lifting. Be explicit about a priori versus a posteriori choices. You must show where you were free to pick scales and patterns before looking at the cold spot, and where choices were made after seeing the data for example during null rotations and scale scans. If you blur that line, your quoted sigma will be biased high. And don't double count large-scale modes. The template fit and any local CL of TG measurement draw from the same sky power, so report how those tests are correlated rather than treating them as independent. KSZ and bulk flows. Even if a void isn't massive enough to create strong lensing or a big ISW dip, moving matter can still nudge the CMB through the kinematic Sunyaev-Zeldovich effect, or KSZ. Here's the idea. CMB photons Thomson scatter off free electrons that have a line-of-sight peculiar velocity, call it V parallel, relative to the CMB rest frame. Each scatter adds a tiny Doppler shift. In other words, the temperature change following delta T over T is proportional to minus 2 sub E times V parallel over C, where 2 sub E is the electron optical depth and C is the speed of light. Galaxy clusters, rich in hot electrons with coherent inflow or outflow, can leave microkelvin level KSZ signals. Filaments and voids also contribute, but more faintly and with mixed signs, because velocities flip direction along the line of sight. Why bring KSZ into Eridanus? Because a genuine supervoid ought to host coherent outflows. Galaxies and gas slowly accelerate away from the underdense center. In principle, that creates a very broad, low-amplitude KSZ pattern. Slightly negative, cold, if the bulk flow points away from us. Slightly positive, hot if toward us. Modulated by the electron distribution in the warm-hot intergalactic medium, WHIM. If you could measure a ring-like KSZ signature with the right sign pattern around the reconstructed void center, you would gain an independent dynamical confirmation that something big and empty is there. In practice, void scale KSZ is hard. First, TET is tiny outside clusters. Most baryons in voids are tenuous, warm gas with low electron densities. Second, the KSZ signal is frequency independent, like primary CMB and ISW, so you cannot spectrally isolate it. You must rely on spatial filtering and cross-correlation. Third, the sign flips with velocity. It integrates along hundreds of megaparsecs and opposing flows can cancel. That is why the cleanest KSZ detections to date stack many halos or reconstruct velocity fields statistically rather than chase single degree-scale features. Here are two practical KSZ tests for Eridanus in clean, read-aloud form. First, the projected field KSZ test. Reconstruct the three-dimensional velocity field from galaxy redshift data using the continuity equation. Density growth implies flows. Then multiply that velocity, EV hat, by an estimate of the free electron density and project it along the Eridanus cone. Cross-correlate that sky template with high-resolution CMB temperature maps from Planck, the Atacama Cosmology Telescope, and the South Pole Telescope. If the correlation is positive, you've detected KSZ power from moving electrons. It won't isolate Eridanus by itself, so gate the test to that patch and compare the amplitude against many random patches with similar masks to see if Eridanus is unusually strong. Second, the pairwise KSZ around void edges. Select galaxies in shells around the reconstructed Eridanus underdensity and measure the mean pairwise momentum, a KSZ statistic, versus separation. In words, you're asking whether galaxies on opposite sides of the shell show a systematic Doppler pattern consistent with outflows from a real void. A genuine void predicts a characteristic sign and scale dependence for this statistic. If the data match that template, it's strong, independent evidence that coherent flows around Eridanus are stirring the CMB. Intruders need to be managed. Thermal SZ from groups along the line of sight has a clear frequency spectrum. Separating the different frequency components can stop it, but leftover TSZ leakage can cause KSZ estimators to be off. Radio sources and dusty galaxies, cosmic infrared background, add small amounts of power that can get into KSZ reconstructions if they are not treated very carefully. It is important to use foreground templates and null tests, like switching the signs of motion, moving galaxies around, or using B-mode KSZ estimators that should go away. What could KSZ tell us about the cold spot itself? Even in optimistic scenarios, void scale KSZ amplitudes are microkelvin or less, an order of magnitude shy of the cold spot's core depth. That means KSZ cannot be the main coolant. However, it can corroborate dynamics. If velocity templated KSZ agrees with an outflowing, underdense Eridanus cone, then the geometry needed for a modest ISW imprint gains credibility. If KSZ refuses to show coherent outflows where the density map says it should, one of the reconstructions, density or velocity or electron distribution, is wrong, and claims of an extreme unified supervoid weaken. Bulk flows add a layer that goes well with it. Large-scale motions can be mapped using peculiar velocity surveys, which can be done without KSZ and use distance markers or forward modelling of redshift space anomalies. The supervoid theory would be supported by a statistically significant increase in outward odd velocities centred near the Eridanus cone. A normal velocity field would suggest that any underdensity is not deep or coherent enough to cause unusual dynamics. By comparing the direction and strength of these flows with the KSZ inferred momentum field, we can see that matter, electrons, and motion all fit together in a single, testable story. Bayesian model comparison. When one sky patch looks impossible, compare explanations in a Bayesian head-to-head and let Occam's razor decide. The contenders for Eridanus are H0, lambda CDM plus statistical noise, i.e. the cold spot is a rare fluctuation. H void lambda CDM plus ISW/RS from a specific underdensity, i.e. a supervoid cools it. H tex lambda CDM plus one cosmic texture, a relict effect, and HSS, residual systematics or foreground. Each has parameters, location, size, depth, and compensation for a void, symmetry breaking scale and profile for a texture, nuisance templates for systematics. The evidence for a model, call it Z, is the likelihood times the prior, integrated over all parameter values. The Bayes factor B sub ij equals Z sub I divided by Z sub j tells you which model wins after paying for freedom. Build a joint data vector with mostly independent pieces. 1. CMB temperature filtered to the cold spot scales. 2. Collocated E-mode polarization. 3. CMB lensing kappa. 4. Large-scale structure reconstructions, delta of sky position and redshift inside the Eridanus cone from galaxies and AGN. And 5. Survey quality templates for dust, stars, depth, and seeing. Use a Gaussian or simulation calibrated likelihood that carries the covariances between these fields, so you don't double count the same large angle modes feeding temperature, kappa, and the ISW prediction. H0 pays little Occam tax, no localized parameters. H void predicts a template. Given delta with uncertainties, forward model the gravitational potential phi, its time derivative phi dot, and lensing kappa to get a temperature profile TISW plus RS and a matching kappa profile. Keep only small nuisance freedoms like galaxy bias and photo-Z scatter with external priors, and do not scan centers and radii after looking at the cold spot unless that search volume is fully accounted for in the prior. H-tex carries a compact profile family, amplitude set by the symmetry breaking scale, angular radius, sign, and a sky uniform prior on positions. Its Occam bill includes allowed spot sizes and the expected number of textures. Compute Z with nested sampling, multi-nest or polychord, or thermodynamic integration on a simulator anchored likelihood. For H-void, propagate the full posterior of delta. Draw many realizations consistent with masks, bias and photo-Z, build the template each time and marginalize to get Z sub-void. For HSIS, include amplitudes for nuisance maps, dust residuals, depth, striping, with conservative priors, and see whether the best fits recur in rotated control patches. If they do, evidence tilts toward it's the instrument or sky, not cosmology. Then run posterior predictive checks. Condition on each model's best fit. Simulate many masked, beam-convolved skies and ask how often your pipeline recovers a wavelet amplitude and radial profile as extreme as observed. A model can win on raw evidence, yet fail these out-of-sample tests if it's overfitting noise quirks. Two sharp corrections matter. Look elsewhere. If Eridanus was chosen because of the cold spot, the prior on a void or texture center must be uniform over the usable sky, not delta peaked on the observed position, otherwise the evidence is inflated. Polarization veto, a texture that mimics primary last scattering physics, should be penalized if the co-located E-mode pattern is absent. H-void should not be punished for that, since ISW and RS are temperature only at first order. If B sub-void, 0 is much greater than 1, while B sub-tex, 0 is much less than 1. The data favour a late-time gravity explanation from a measured trough. Lambda CDM survives, but only by allowing a razor-tail supervoid that matches kappa and LSS. If B subtext 0 is much greater than 1 and kappa and LSS show no trough, the texture story gains ground, provided its required abundance fits full sky limits. If both B subvoid 0 and B subtext 0 are less than or about 1, Occam's razor wins, and H0, a rare fluctuation, remains the sturdy, if dull, champion. And if B sub cis 0 is large, you've likely rediscovered a foreground or residual, meaning the cold spot shrinks with better cleaning. The scary Bayesian ending. After you pay every prior and look elsewhere bill, all Bayes factors may be only modest. Then the anomaly is interesting, but not decisive, until sharper kappa maps, denser spectroscopy, or cleaner polarization tip the scales. Suspense builder, if, after full penalties, only a finely tuned, elongated void ties just noise, either we live in the tail, or a missing hypothesis hasn't entered the ring yet. Cosmic texture. Hypothesis. There are mathematical flaws called cosmic textures that happen when a high-energy symmetry breaks in the early universe. Textures are not steady like strings or domain walls. They unwind, letting go of a gravity potential that changes over time that CMB photons travel through. This changing potential makes hot or cold spots in specific areas by using a Sachs-Wolfe-like shift that is purely gravitational and has angular radii of a few degrees. Because of the cold spot's size, consistency, and lack of colour, patterns were quickly ruled out as a possible cause. At first glance, the Eridanus alignment seems like a good fit. A cosmic texture predicts a compact, self-similar temperature profile with a central hot or cold extremum and gentle compensation, well described by a 1 or 2 parameter template, an amplitude tied to the symmetry breaking scale, and an angular size set by theta star. Because the signal is gravitational and arises long after last scattering, it should carry little to no co-located E-mode polarization of the kind seen with primary hot-cold spots. and it should not track nearby large-scale structure, no required galaxy underdensity, and no strong kappa dip, beyond a tiny transient potential lensing signature. A concrete texture model also predicts how many such spots should be detectable across the sky. So fitting one prominent spot usually implies there ought to be others at lower contrast. Testing follows that logic. First, a morphology test. Fit the texture template, with theory-motivated priors on amplitude and theta star, to the cold spot in clean CMB maps using match filters, and score the likelihood gain against Gaussian skies while properly penalising the freedom to scan positions and radii. Second, a polarization test. Extract the local E-mode map and compare it to what a primary feature would imprint. A null-like E pattern is consistent with a texture and with ISW/RS, while a strong correlated E signal disfavours any late-time origin. Third, an LSS and lensing check. If a texture is cooling the spot, galaxy counts and kappa toward Eridanus should look ordinary once systematics are controlled. Any significant negative kappa or coherent underdensity weakens the texture case and instead supports a void-driven ISW explanation. There are also limits on the full sky. By using ideal filters and Bayesian model selection to look for textures across WMAP and Planck maps, upper limits are set on the number and magnitude of events that can be found. A cold spot level detection must happen while there aren't many brothers present elsewhere. If the symmetry breaking scale needed to match Eridanus forecasts too many strong spots, the model is thrown out. On the other hand, if the expected counts are very low, it is unlikely that we found exactly one bright one, unless the priors are made bigger, which is another Occam cost. Potential confusions abound. A compensated supervoid filtered with a wavelet can mimic the ring and core appearance of a texture. Both are achromatic and weak in polarization. Distinguishing them hinges on correlated evidence, lensing kappa and LSS tomography, void, versus null kappa/LSS, and a better morphological fit, texture. Systematic residuals, e.g. foreground cleaning artifacts, can also create degree-scale depressions. Textures survive only if the feature is stable across component separation methods, frequency splits, mask choices, and beam systematics. And if control patches with similar masks do not show equally striking textures at comparable rates. How would a texture win look? We found a strong template match in temperature along the radius limits. No co-located E-mode excess beyond lambda CDM expectations. No significant negative kappa depression. And flat galaxy/AGN/quasar counts within honest completeness errors. It becomes very important that the case works with global texture counts and amplitudes. It looks like the opposite of what you'd expect. Good template fits, but not dominant ones. A small kappa dip or LSS trough that won't go away. And Bayes factors that favour either rare Gaussian fluctuation or void-induced ISW. Modified gravity checks. Could gravity itself be slightly different on cosmic scales, making an Eridanus-type trough deeper, faster growing and more efficient at chilling the CMB than lambda CDM with general relativity GR predicts? That's the modified gravity angle. Families like FR gravity chameleon screening, DGP/N, DGP Weinstein screening and scalar tensor, or Galilean models tweak the growth of structure and the relation between the two gravitational potentials, the gravitational slip. Voids are prime arenas because screening often weakens in low-density regions. Effective forces can be enhanced, pushing matter out more vigorously and making void interiors emptier and their outflows stronger. If Eridanus lives in such a regime, the same observed galaxy deficit could correspond to a larger mass deficit and a bigger late-time integrated Sachs-Wolfe ISW imprint than GR would infer. To stress test this idea, use 3 linked observables. First, growth history. Modified gravity changes the linear growth rate and amplitude. Think f of z and sigma 8 of z, which sets how fast voids evacuate. Redshift space distortions measure f times sigma 8, so if the Eridanus cone needs unusually rapid local growth to reach its depth, it must still respect global f sigma 8 limits. Second, lensing versus dynamics. In general relativity, lensing feels phi plus psi, while motions feel psi, tying the two. Modified gravity can introduce a gravitational slip. ETA equals phi over psi not equal to 1. Use the EG statistic and combine void lensing plus RSD tests to ask, does the mass profile from galaxy motions and counts predict the same weak lensing convergence and shear? A void that looks too lensy for its counts, or not lensy enough, flags non-GR responses or unmodelled bias. Third, the ISW kernel. The temperature shift depends on phi dot plus psi dot, and modified gravity can change both its strength and the redshift window where it peaks, shifting which voids most efficiently cool the CMB. A disciplined test then: 1. Reconstruct delta of sky position and redshift with bias uncertainties. 2. Forward model phi, psi, their slip, and time derivatives under both GR and specific MG models, like f of r with parameter FR0, Bianchi DGP with crossover scale RC, or a Horndeski EFT basis. 3. Predict observables: CMB lensing kappa, galaxy shear in tomographic bins, an Eridanus specific ISW temperature template, and RSD outflow signatures around the void edge. 4. Fit them jointly in the Eridanus patch and against global constraints from RSD, BAO, full sky kappa spectra, and galaxy kappa cross correlations. 5. Finally ask, does any modified gravity parameter set that passes global tests also produce an ISW plus lensing signal strong enough to explain the cold spot, given the measured delta? Screening physics matters for the verdict. In chameleon-screened f of r, the effective gravitational strength is enhanced in voids, deepening them and boosting outflows. This can increase void lensing and slightly elevate void ISW. In Weinstein-screened DGP-like models, forces recover GR around massive bodies, but can deviate in low-density environments with distinct signatures in velocity fields and a different slip pattern. Either way, consistency across probes is non-negotiable. An MG that makes Eridanus's ISW big enough must not simultaneously overpredict kappa lensing or violate RSD growth constraints globally. That tension is often what prunes MG explanations down to small corners of parameter space. Some important mistakes you should not make are tuning after the fact. Picking MG parameters because they help Eridanus doesn't mean anything unless those parameters already pass global tests. The Occam tax in a Bayesian comparison will destroy such ad hoc fits. A. Mixing up tracer bias with gravity, a bigger empty space that you might see in blue galaxies that are making stars could be caused by developing bias instead of deeper mass loss. Anchor BZ with external clustering and galaxy kappa cross correlation, and push those unknowns to the side. Not taking into account compensation, MG can change how sharp void ridges get. A stronger ridge can cancel out ISW wins from a lower core. The measured pay description needs to be in your template. There are 2 smoking guns that point to MG. Detecting slip at the void scale, the lensing to RSD ratio, or EG, in the annuli around Eridanus is different from GR in the same way that the MG model used to improve ISW needs it to be. B. Velocity lens synergy, unusual velocity predictions from RSD or reconstructed flows, show outflows that are stronger than GR and match in size and volume with a higher kappa dip in the void. On the other hand, making gravity stronger in voids, can't be the secret coolant if Ki and gamma T match GR forecast from the galaxy's mass and RSD growth looks normal. Simulated light cones. We can tell if claims about rare supervoids and cold spot level ISW signs are true or false by looking ahead. Can a reasonable lambda CDM or MG universe make an Eridanus-like line of sight often enough when you look at every survey wrinkle and analysis choice? This is what simulated light cones give you. Fake worlds you can observe with the same cameras, masks, photometric scatters and pipelines. Then you can check to see if your result in the real sky is unusual or what you would expect. Build starts with large n-body boxes, or fast approximate methods calibrated to them, spanning tens of billions of light years to capture ultra-rare structures and large-angle modes. From snapshots, stitch a light cone that follows past light paths to Z approximately 2 to 3. The regime relevant for ISW and most traces. Populate halos with galaxies and AGN via HODS or semi-empirical models matched to luminosity/color functions. Paint radio and X-ray sources where needed. If testing MG, run dedicated MG simulations with screening solvers or apply accurate response functions to GR fields, crucial for void interiors. Next, ray trace the sky. Compute the full lensing convergence, say kappa, and shear, gamma, by integrating the possibly modified gravity potentials along the light cone, going beyond the Born approximation if you need nonlinear accuracy. In parallel, compute the ISW plus Rees-Sciama temperature by integrating phi dot plus psi dot along CMB lines of sight. Then add a primary CMB realization consistent with the same cosmology and lens it with the ray trace kappa to generate realistic temperature and polarization maps. Those simulated maps, together with the underlying kappa, gamma, and potential fields, are your truth fields. Then watch the survey. Use the real sky mask to see things like bright stars, changes in depth, seeing, galactic extinction, and scanning tracks. Change the intrinsic magnitudes of galaxies to those that have been spotted with noise. Get rid of those that are below the depth map. Add photometric redshift errors with real-world scatter and catastrophic outlier tails that depend on color and magnitude. For radio/IR/X-ray traces, set limits on flux, completeness, and angular patterns like striping and moon contamination that look like NVSS or WISE effects. Make component-separated CMB maps by mixing frequencies with leftover foregrounds at the right level. This way, your study will have to deal with the same cleaning problems. Now, run the identical pipeline used on the data. Cut the Eridanus size cone everywhere on the mock sky. Perform tomographic reconstruction of delta theta Z with the same binning. Apply the same void finder and linking criteria. Calibrate galaxy bias with the same cross correlations, and build the same template for kappa and ISW. Apply matched filters to the mock CMB temperature and kappa maps, and record the best fit amplitudes. Critically, let the pipeline scan over centering, radius, and compensated profiles to the same extent it did on the data, so the look elsewhere effect is paid automatically. What do you measure from these mocks? I, the extreme value distribution of trough strengths and template amplitudes across the sky. I, the joint distribution of AT, are kappa template fits, capturing correlations between LSS and CMB, Redshift. The frequency with which a trough that looks like a single tunnel in photo Z tomography is actually a stack of voids when examined in truth. Quantify the misidentification rate. I've the impact of compensation. How often a strong ridge cancels an apparently deep interior in ISW. And V, the rate at which systematics, depth/seeing/dust residuals, radio striping, forge false underdensities that pass naive cuts but fail lensing. Two technical choices make the story more trustworthy. First, think about the size of the ensemble. To look into percent level tails, you need thousands of full sky, or at least many steradian light cones. Tiling or spinning boxes must keep large-scale modes and avoid repeating structures. Second, divide the variance into three parts. A. Truth field analyses, no masks, no photo Z. B. Mask truth analyses, and C. Full observed like analyses. This will help you tell the difference between cosmic variance and pipeline/systematic variance. The tails getting wider from A to C is your analysis cost. You can only claim a real p-value for Eridanus if you include it. If, under general relativity with a Planck-like cosmology, cold spot scale temperature dips with near zero kappa show up often enough in simulations that include look elsewhere freedom and real survey noise, then the cold spot is statistically comfortable as a fluctuation. If not, if matching both the observed temperature depth and the reconstructed delta of sky position and redshift demands either A, an unusually coherent undercompensated tunnel that also appears in weak lensing kappa and gamma, rare but allowed in lambda CDM, or B, modified gravity parameters pushed near current bounds. Then the anomaly is pointing somewhere specific, either to a tail event supervoid within lambda CDM, the void culprit, or to beyond GR tweaks that change growth or the ISW response, the gravity culprit. Void evolution and profiles. A void is not just an empty space. It's a dynamical structure whose inside grows faster than the average universe and whose edge, called a ridge, controls the flow of momentum with the web around it. In lambda CDM, underdensities get less dense because gravity pulls on matter outside the void more strongly than on matter inside it. This causes matter to move steadily from the center to the edge. There are two developmental paths that set the scene. In a void-in-void situation, the low-density area sits inside a bigger low-density area and keeps growing, making the difference stronger. In a void-in-cloud situation, an overdensity around the void slows its growth over time and often creates a strong wall to make up for it. The maximum size of Eridanus's gravity pull is determined by the direction it takes. Profiles matter because they map to potentials, velocities, lensing, and the late-time integrated Sachs-Wolfe ISW effect. Empirically, stacked voids exhibit a universal shape, a gently sloping, low-density core that rises toward a narrow ridge near a characteristic radius, then relaxes to the cosmic mean. A compact parameterization uses a central contrast delta C delta C, how empty the center is, a scale radius where the profile turns up, and outer slope parameters that set the ridge height and width. For ISW, the integral of the potential, not just density, and its time derivative matters. A deep, undercompensated profile, weak or distant ridge, produces a larger net temperature dip than a deep but compensated one, where the ridge cancels much of the void's core imprint and can even generate a faint hot ring around a cold center in filtered CMB maps. Kinematics trace the same physics. The mean radial peculiar velocity is outward inside the void, peaking near the core ridge transition where the density gradient is steepest, and then tapering towards zero or mild infall beyond the ridge. In redshift space, this creates a characteristic quadrupole in the void-galaxy correlation. Outflow squashing along the line of sight inside the void and possible infall stretching near the ridge, depending on the environment. Measuring that pattern in Eridanus via void-centric redshift space distortions, RSD, test whether the reconstructed trough is dynamically coherent, one evolving structure, or a blur of unrelated dips created by photometric redshift smearing. Time evolution adds two amplifiers to the effect. First, as dark energy begins to dominate at redshift less than or about 1, the gravitational potential hills linked to cosmic void start to decay, creating a temperature drop in CMB photons that pass through them. This is the linear integrated Sachs-Wolfe effect. Second, nonlinear growth slightly reshapes those potentials through the Rees-Sciama correction, which deepens the central cold dip and tweaks the balance of any surrounding warm ring for especially deep, evolving voids. Both amplifiers depend on geometry. An elongated trough aligned with our line of sight lets photons stay inside the changing potential longer, boosting the temperature shift, while a narrow, overcompensated ridge cancels much of that gain. Baryons and neutrinos modulate profiles subtly. Hot gas avoids void cores, preferring walls and nodes. The warm-hot intergalactic medium, DWM, accumulates near ridges where shocks and accretion heat it. That shifts where kinematic SZ signals could appear, mostly in shells, and it means that free electron optical depth, and therefore any void scale KSZ will be small in the interior. Massive neutrinos, with large thermal speeds, partially wash out small voids, but leave degree-scale troughs mostly intact. However, they can slightly change the relation between galaxy contrast and total matter contrast, a nuisance to propagate when turning counts into potentials for Eridanus. For Eridanus, 3 profile checks decide the case. First, core versus ridge, a cold CMB center with only a faint warm ring after wavelet filtering points to an undercompensated or gently compensated void. A strong warm ring with a shallow core implies overcompensation that cancels the ISW signal. Second, continuity through redshift, a single, slowly evolving minimum that tracks smoothly across tomographic slices signals a real tunnel, while hops between separate minima reveal a stacked alignment that won't add coherently in ISW or lensing. Third, velocity coherence, a void-like RSD quadrupole centered on the same sky position and radius as the density trough confirms a unified dynamical structure. If coherent outflows are missing, the mass deficit is weak or the environment is compressing it. A void in cloud. Modeling must be forward and joint. Start from the measured 3D galaxy field, carrying bias and photo-Z uncertainties, and infer a posterior over void profile parameters. Delta sub C, central contrast, R sub S, scale radius, and ridge strength as a function of redshift. Propagate that posterior into predictions for kappa of theta, lensing convergence, gamma sub T of theta, tangential shear, and delta T ISW plus RS of theta, temperature. Fit these specific templates simultaneously to CMB lensing, galaxy shear and temperature with centering, smoothing and mass choices pre-registered to avoid a posteriori inflation. The question isn't, does a generic void correlate with the cold spot, but does this evolution-consistent profile with this level of compensation reproduce the observed radial shapes and amplitudes across all 3 fields? Pitfalls can be seen coming. Surrounding ridge stacks with too much water turns them into undercompensated tunnels on paper. Ignoring depth, seeing, dust systematics makes fake ridges out of masks. Off-centering by even half a degree can wipe out lensing and RSD signals. And photo-Z blur increases predicted ISW beyond what spectroscopy would allow. To protect each one, end-to-end mocks that go through the same process must be used. If Eridanus's best fit profile ends up deep but strongly compensated, the gravitational ledger says the ISW should be modest, and the cold spot must be largely primordial or statistical. If it is deep and undercompensated, dynamically coherent across redshift, and elongated along the line of sight, the late-time gravity case strengthens, provided lensing and RSD agree. Suspense builder. Once the profile is nailed, there's nowhere to hide. Either the measured evolution can carve a crater that big, or the cold spot's chill comes from somewhere evolution cannot reach. Surrounding structures and walls. There is no void that lives by itself. Sheets, filaments and superclusters shape its boundary conditions, which determine whether it opens up into a straight tube or is cut up into pieces by walls. The large-scale neighbourhood around Eridanus is more than just scenery. It controls things like compensation, lensing form, kinematics, and even the chance of mistaking a stacked passage for a single supervoid. Start with compensation architecture. A void bordered by one dominant wall acts like a bowl with a single high rim. CMB temperature profiles then favour a cold centre with a one-sided hot ring and an asymmetric tail. A void encircled by a more isotropic overdense shell behaves like a donut, strong compensation all around, and its ISW imprint shrinks, while its lensing convergence acquires a dip and bump signature, negative kappa inside, shallow positive kappa just outside. If Eridanus sits between two or more supercluster spines, you can get multiple hot ring shoulders in a wavelet filtered map and a more complicated shear pattern. Mapping these ridges in 3D is therefore not optional. It is the control knob on every predicted observable. Then consider line-of-sight percolation. Photometric redshift smearing can link multiple moderate voids separated by thin walls into an apparent continuous trough. Spectroscopy typically reveals the truth. Weak overdense sheets slice the corridor, interrupt outflows, and spoil coherent ISW addition. A telltale sign is a bimodal distribution of cluster and group redshifts along the cone, peaks at the wall redshifts, troughs in between. Cross-matching with cluster catalogues, optical richness, X-ray and TSZ localizes those walls. If rich clusters sit right where the tomographic trough pauses, the environment is actively segmenting the line of sight and downgrading the supervoid hypothesis. The same lines show up in gas physics. The walls of superclusters hold baryons that are hotter and denser. Compared to the cores of clusters, they glow in thermal SZ, Compton I, and X-rays at lower levels, and they provide most of the free electrons that power KSZ signals. To test Eridanus in the real world, look for circular TSZ increases around the supposed void radius. A Y-ring that is too strong means that the tunnel is adequately compensated, while a Y-ring that is not present is better for an undercompensated tunnel. In the same way, projected field KSZ reconstructions should pick up coherent outward motion close to the edges of voids. Signs that are mixed or disappear suggest that the environment is broken up. In a clean tunnel, galaxy peculiar velocities point outward from the center across a wide solid angle. In a pinch corridor, the velocity field changes sign near walls, outflow inside, infalling onto the sheets. Redshift space multipoles of the void galaxy correlation, measured in shells, reveal that transition. If Eridanus's surroundings enforce strong infall within a few degrees of the center, predicted ISW and lensing templates must include that compensation. Otherwise, void-only models overpredict the cold spot's depth. A further environmental lever is bias ecology. Galaxy types populate environments differently. Quiescent, massive galaxies cluster near walls. Blue, star-forming galaxies more readily trace low-density interiors. Counting only one type can misweight compensation. A robust Eridanus map should show the same underdensity after bias correction in red and blue samples. In radio-loud AGN, which prefer massive hosts near walls, and in quasars, which reach higher redshift. Disagreement that tracks environment signals selection, not mass. Tie the picture together with three map types. First, do counts in anomalies tomography. Measure galaxy contrast in concentric, co-moving shells at successive redshifts and watch how the ridge behaves. One broad, modest ridge supports undercompensation. Several sharp peaks at different redshifts reveal sliced walls masquerading as one void. Second, build multi-probe shells, stack thermal SZY, weak lensing tangential shear, and CMB lensing kappa in the same anomali, and compare their phases. A clear Y peak with little kappa suggests hot gas on thin sheets without enough total mass. A kappa bump without Y hints at dark walls or low gas fractions. Third, map cluster and filament skeletons with graph-based filament finders to trace the web around Eridanus. If the void center sits inside a not-rich junction, expect strong compensation and a weaker ISW effect. If it lies in a long, clean tunnel of the web, the supervoid case becomes stronger. Mask and survey edge systematics can imitate the environment. A sharp drop in depth along one side of the cone plus bright star masks along another crafts a fake ridge. Rotating the entire analysis to many control cones with identical mask complexity is the antidote. A genuine environmental ridge pattern should not repeat at high rates in those controls. Galaxy ecology in voids. Not only do underdense areas have fewer galaxies, they also have different kinds of galaxies. In places with low density, galaxies tend to be late-type, blue, gas-rich systems that have higher specific star formation rates, SSSFR, at given mass, lower stellar masses on average, and lower metallicities in the gas phase. That ecosystem forms because the normal things that stop growth, cluster tides, ram pressure stripping, and repeated mergers, happen less often. Cold gas lasts longer, inputs are less slowed down, and disks keep quietly making stars. The census of Eridanus should tilt in these exact ways if it really does have a big, coherent trough. If it doesn't, the mass deficit that can be drawn from counts may be partly a tracer error. Start with star formation. SSFFR from UV plus IR or H alpha tends to be higher for void galaxies than for peers in walls at the same stellar mass. The effect isn't huge, but it is consistent. More fuel, less harassment, slower quenching. A practical test along the Eridanus cone is to build volume-limited samples in narrow stellar mass bins and compare SSFFR distributions inside the trough versus matched control cones. A genuine void should show a shift toward longer star-forming duty cycles and a deficit of fully quenched systems at fixed mass. Because blue star-forming galaxies have lower large-scale bias than red, quenched ones, this ecology feeds back into mass inference. Pure blue-selected catalogues can overstate the depth of a void unless you correct for the evolving bias. Metallicity tells a story that goes well with it. In sparse settings, the mass-metallicity relationship is shifted to lower OH at given mass. This is because chemicals are being added more slowly and/or more fresh gas is coming in. It is possible to check this with strong line estimates of metallicity with a single calibration to avoid method mixing across the Eridanus cone. There is a consistent pattern of low metallicities in following redshift slices. This makes it more likely that we are looking at a long, gentle tunnel instead of a collection of normal environments. If metallicities look like walls, higher O/H, more metal-rich dust. But counts say there is nothing there, it's likely that selection or hiding is at work. Morphology and kinematics are next. Disk fractions should rise, bar fractions may be modestly lower, and merger signatures rarer in the trough. Machine learning morphologies on deep imaging, trained per field to handle seeing changes, can quantify this. Misclassifications near the galactic plane must be modelled because stars masquerade as compact disks. On the kinematic side, Tully-Fisher residuals and rotation curve shapes of HI-rich disks inside the cone should look entirely ordinary. That is the point. Voids don't break internal dynamics. They change the mix of galaxies present. What can change is the distribution of rotational axes and subtle outflow patterns near a compensating ridge, detectable statistically via redshift space distortions in void-centric stacks. Neutral hydrogen is the ecological linchpin. HI fractions rise in underdensities, and HI selected samples, e.g. alfalfa-like depths, overrepresent void interiors. That is a feature if you want to map gas reservoirs. It's a bug if you convert galaxy counts to mass without a bias model. A clean Eridanus program therefore cross-matches optical/IR and 21 cm selections, derives HI to stellar mass ratios MHI/M* as a function of position, and asks whether gas richness climbs steadily through the trough and ebbs near the ridge. A rising MHI/M*, MHI/M* gradient across multiple redshift slices would be a smoking gun ecological signature of a true continuous underdensity. Radio ecology and AGN add depth. AGN that are radio loud like huge hosts that are in denser settings. This means that a radio deficit toward Eridanus can show more than just how much mass is there. On the other hand, quasars that are visually chosen and not hidden are less affected by their surroundings at a constant brightness, but look deeper into higher redshifts. They should thin out a bit if the trough really integrates far. The cross-tracer rule is easy to understand. If radio-loud AGN drops strongly, blue disks rise, HI detection surge, and red galaxies that are not active fade, all in the same sky cone and over time, then the ecosystem fits an extended void. If tracers don't agree on how to choose a track, for example, mid-IR AGN only dips under one color cut, then systematics takes over. How does ecology feed the cold spot physics? Through bias, compensation, and template shape. A trough dominated by low bias blue disks and HI galaxies can look deeper in counts than in mass. Correcting for that weakens the predicted late-time ISW signal. On the flip side, an undercompensated profile, weak ridge, implies fewer quenched, massive galaxies in the shell, and therefore fewer radio-loud AGN just outside the void. Exactly the ring where a wavelet-filtered CMB map might show a faint hot shoulder. If the observed shell is rich in massive red systems and TSZ bright groups, compensation is strong, and the ISW cancellation larger than a galaxy-only model would assume. Measurement traps are fixable but real. Dust and seeing gradients bias color cuts and star-galaxy separation, manufacturing apparent ecology shifts, mitigate them with per-exposure depth maps, stellar density regressions, and forward simulations that inject fake galaxies with a realistic size-color surface brightness distribution. Photometric redshift outliers move blue dwarfs across bins, seeding fake gas-rich cores. Anchor NZ with clustering redshift calibration against spectroscopy. HI catalogues have complex completeness surfaces versus line width and flux. Use injection recovery to build effective volumes before comparing MHI/M*, MHI/M* across the cone, and always rotate the entire analysis to dozens of control cones with identical mass complexity to estimate how often ecology shifts appear by chance. ArchI 21 cm views. Neutral hydrogen quietly maps out the cosmic web. As of recently, the hyperfine 21 cm line has made it possible to find gas-rich galaxies one at a time, discrete detections, and measure the total HI as a fuzzy light field, intensity mapping. As a near-ideal cross-check for an Eridanus Supervoid claim, HI should show that void interiors have more HI-rich, low-mass rings per unit star mass. However, the total HI mass along the line of sight should still be lower than average, because there is less matter. Seeing both effects clearly tells the difference between tracer bias and a real mass loss. It also shows where gas builds up on adjustment walls. Start with the HI surveys. Legacy blind maps, HIPASS in the south and ALFALFA in the north. Cover ZR less than about 0.06 with uniform selection and well-tested completeness in integrated flux and line width. New programs extend area or depth. ASKAPs a wallaby, wide, Z less than about 0.26. Meerkats, MHONGOOSE, deep nearby galaxies, and LADUMA, ultra-deep single field, pushing HI to Z about 1, plus APERTIF in the north. Toward Eridanus, the playbook is define a clean cone that avoids strong galactic emission. Compile HI detections with robust fluxes and W50 line widths. Build volume-limited subsamples in narrow W50 and stellar mass bins to tame Malmquist bias. Then compare the HI mass function, the gas to stars ratio MHI over M star, and detection fractions inside the cone against matched control cones. A true underdensity should show higher MHI over M star at fixed M star, the classic void ecology, but a lower integrated HI mass density, say RHO sub HI, along the line of sight, signalling a mass deficit. If compensation is strong at the ridge, expect those regions to light up with more massive HI-rich groups and a tilt toward broader line widths. Selection physics matters. HI completeness falls with narrow profiles and low flux. Beam confusion near the galactic plane blends sources. Radio frequency interference carves frequency notches that masquerade as redshift holes. The cure is injection recovery. Plant fake galaxies with a realistic joint distribution of flux size and line width directly into the visibilities or image cubes for the Eridanus fields. Run the same source finder and derive a completeness surface C of SINT, W50C of SINT, W50. Then weight detections by 1 over C, 1 over C before comparing with controls. Also, enforce identical effective depth across Eridanus and control cones by trimming to the shallower completeness. Otherwise, a slightly deeper control field fakes a deficit. Now, intensity mapping. Instead of counting individual galaxies, it treats neutral hydrogen as a diffuse field, keeping even low signal voxels to measure aggregate fluctuations. Arrays like ASCAP, Meerkat, Chime/Hyrax class instruments and SKA pathfinders can map HI power and brightness across redshift 0.1 to 0.8, with coarse angles but excellent redshift precision set by megahertz scale channels. For Eridanus, this gives two clean tests. A tomographic trough. Ask whether the mean HI brightness temperature, set aloud as T sub B of theta, and Z, is depressed along the cone across consecutive redshift slices. And B, a cross-correlation with optical or infrared galaxy samples in the same slices, which both calibrates the HI galaxy bias relation and helps suppress foreground residuals. Foregrounds are the IM nemesis. Galactic synchrotron is orders of magnitude brighter than the HI signal and spectrally smooth. Bright point sources add structure. Instrument bandpass ripples make smooth things look wiggly in frequency. Conservative pipelines project out low-order spectral modes, foreground cleaning, but that also removes long wavelength radial modes, the very modes that trace wide, line-of-sight troughs. Two guardrails keep the Eridanus IM test honest. One, forward simulations with the actual beam, bandpass and flagging pattern for the Eridanus tracks, showing that the measured cleaning leaves enough radial modes to see a 200 to 600 megaparsec trough. And two, external templates. Cross-correlate the cleaned HI cube with a photo-Z galaxy map. The cross-correlation is immune to many IM systematics and will still show a deficit if both trace the same underdensity. Tie HI back to compensation and dynamics. If a supervoid is undercompensated, the HI brightness field should show a broad, shallow depression with only a weak ring. If it's strongly compensated, expect a clearer annular bump in TB just outside the void radius as gas collects on walls. Pair that with thermal SZY maps. A Y ring without an HI ring implies hot ionized gas on thin walls, high temperature, low neutral fraction. An HI ring without much Y suggests cooler, neutral-rich walls with modest pressure. Add galaxy weak lensing kappa over gamma T annuli, and you have a 3-probe phase test: mass kappa, neutral gas HI, and hot electrons Y should align in radius if the environment is real. Misalignment flags selection or cleaning artifacts. What about ISW relevance? HI doesn't directly cool the CMB, that's gravity's job, but it calibrates the bias correction that turns galaxy counts into mass. If the Eridanus cone's galaxy deficit is inflated by a shift toward low bias, gas-rich dwarfs, HI reveals it. Detection fractions rise even as stellar mass density falls. Correcting for that bias reduces the predicted ISW amplitude, potentially demoting the void as the cold spot's main cause. Conversely, if both stellar and HI mass densities drop in lockstep across multiple slices and a modest HI ring marks the ridge, the mass deficit claim strengthens and the ISW template becomes sharper and less tunable. There are 2 potential failure modes to check. First, there is galactic HI leaking. When the speed of light is low, the Milky Way emits a lot of light into the band. Tough masking can create fake redshift gaps. Always record the velocity ranges that were taken out and show that the Eridanus trough still exists when those channels are taken out. Second, beam and scan systematics. Drift scans leave declination-dependent stripes. Imperfect primary beam models change the amount of TB in the field. This is found by nulls that move the cone in right ascension at a fixed declination, same beam, different sky. A real trough shouldn't follow the telescope. A decisive HI verdict would look like this in plain terms. After careful injection recovery tests and match completeness, the discrete HI catalogues show higher gas to stars ratios, say MHI over M star, but lower total HI mass density, ratio HI, along the Eridanus cone than in control regions, and this pattern holds across several redshift bins. The intensity mapping maps, cleaned and validated by optical cross-correlations, reveal a broad brightness temperature dip, T sub B, aligned with the galaxy underdensity, plus a ridge scale bump if compensation is strong. The annular weak lensing and thermal SZ profiles, that is kappa and Y, line up in phase with these HI features. Finally, when you forward model the ISW template from the bias-corrected mass profile, the predicted temperature dip matches the cold spot shape and amplitude within errors. If any of those links breaks, HI mass stays normal while galaxies thin, IM depressions vanish after stricter cleaning, kappa refuses to dip where HI says wall, then the supervoid as cold spot engine loses oxygen. Suspense builder. If the neutral universe won't carve a hole through Eridanus, gravity probably doesn't either, and the cold spot's chill must be coming from somewhere H I can't trace. CMB polarization. The cold spot's lie detector is polarization, which tells the difference between born at last scattering temperature structure and gravity tricks that were added later. When particles collide, they make primary hot and cold patches that have a linked E-mode polarization pattern with a very specific shape and phase that changes with temperature. Late time effects, like an underdensity that changes the integrated Sachs-Wolfe signal, small nonlinear Rees-Sciama corrections, or a cosmic texture unwinding long after recombination, should only affect temperature at the first order and not cause a local E-mode excess to match. That is the main test. Does the cold spot region in Eridanus show the E-mode pattern that would be expected for a primordial temperature dip, or does it look polarization quiet in a way that points to a later origin? The shape that was expected is exact. Write down the Stokes parameters QR and UR in a local radial basis that is set up around the middle of the cold spot. For a main temperature drop on a degree scale, Thomson scattering finally produces a tangential radial polarization pattern, where QR changes sign at a characteristic angular radius, and UR stays the same on average. In the same way that there is a non-zero full sky TE cross-correlation at low multipoles, temperature and E mode are not separate if they both appear at the last scattering surface. The underlying acoustic phase and the smoothing scale determine the magnitude of the local pattern. However, the pattern must appear and have a phase. The ISW shift, on the other hand, happens when gravity potentials decrease, while a CMB photon moves through large-scale structure at redshifts much lower than 1. There is no new Thomson scattering event, so no local E-mode partner is created. As a late evolving potential, a texture also acts gravitationally and achromatically, leaving temperature without an E-mode trace that is also present. Turning this principle into a decision requires careful filtering because polarization maps are noisy on the very large angular scales relevant to the cold spot. The disciplined approach starts by fixing the analysis choices a priori: beam smoothing, the aperture or wavelet scale, the center derived from temperature alone, and the mask apodization that limits galactic leakage. With those set, one constructs a matched filter for the predicted E-mode pattern based on a lambda CDM sky, conditioned on the observed large angle temperature field outside the test patch, so cosmic variance is not double counted. Applying that filter to multiple independently cleaned polarization maps tests for a co-located E-mode excess with the correct sign and radial phase. The significance must be calibrated by rotating the same filter to many random sky positions with comparable mask complexity. This rotation ensemble captures the look elsewhere effect intrinsic to any patch test. A complementary test works in harmonic space but is still localized in the sky. Using pure E estimators to control leakage from masked Q/U maps, one measures the temperature E cross-correlation restricted to an apodized window around Eridanus and compares it to the distribution obtained by sliding the window to other locations. If the cold spot is a primordial fluctuation, the local TE correlation should look ordinary, possibly even a bit enhanced, relative to typical patches at the same galactic latitude and mask. If it is a late-time feature superposed on a random temperature field, the local TE should be depressed, because the spot's temperature power is not accompanied by matching E-mode power. These fingerprints can be faked or erased by systems, so the check is just as important as the measurement. Galactic dust that is polarized is the main pollutant. It has a frequency range and spatial association that are different from the CMB. A real CMB polarization signal needs to stay the same across component-separated maps that use very different linear combinations of frequencies. The amount of dust that is still there changes depending on the frequency mix. The instrument beam and scanning strategy can connect E and B modes or add stripes. Before any local detection is accepted, half-mission null tests and detector set splits should be passed. When it comes to a main spot, the expected profile is 0, so acts as an internal null channel. An profile that is strongly aligned with the temperature dip indicates leaks or random alignments, instead of the clean primordial geometry. Rionization adds subtlety, but not confusion. Large angle E-mode power receives a boost from rescattering at reionization, yet this is a global effect that raises the background correlation rather than painting a bespoke pattern on Eridanus. A primordial cold spot still predicts a local E-mode geometry superposed on that background, while late-time imprints remain polarization quiet. Lensing also complicates matters only weakly here. lensing converts some E into B, but at degree scales the induced B mode is small and can be used as a cross-check. A local excess of B consistent with dust rather than lensing warns that the patch is foreground-ridden and any E inference is suspect. What would each hypothesis's answer look like? As long as the matched filter E test shows a steady positive amplitude with the right QR phase and the localized TE cross-correlation fits within the lambda CDM expectations for a primordial dip, the cold spot does not need a late-time engine. Even if there was a gap, it would only add a few microkelvin, but most of the depression would have already spread out and ended up in an underdense direction by chance. If, on the other hand, the E-mode tests come back negative within small mistakes and the temperature stays very low, the balance moves toward a late-time cause. That being the case, the rest of the multi-probe program, lens convergence, galaxy tomography, HI intensity mapping, and velocity fields must explain it. A coherent, undercompensated trough that is long and stretched along the line of sight should dent a little thin galaxies across multiple redshift slices and show outflows that look like voids. If those mass mapping signatures don't show up either, a texture template is the most likely late-time option, as long as it fits the temperature morphology and doesn't make too many brothers elsewhere in the sky. There is an uncomfortable third outcome in which polarization data are too noisy or foreground limited to deliver a decisive local verdict. Then the right move is to treat the polarization constraints as weak priors in a Bayesian model comparison, letting the lensing and large-scale structure evidence set the pace, while polarization vetoes only the most egregious primordial fits. Future experiments with cleaner large-angle polarization, both satellite and ground-based, shrink this ambiguity by lowering noise and tightening control of systematics on multi-degree scales. Wavelet and needlet analyses. People know the cold spot better from filtered temperature maps than from raw ones. This is especially true for sphere wavelets, which are used to highlight structures that are both localized in the sky and limited in size. The sphere Mexican hat wavelet became the big deal because it compensates. It emphasizes a central dip while reducing very large-scale drifts, and it naturally creates the cold core/weak hot ring shape that the Eridanus patch seems to have. When you use this filter on a full sky CMB map at a size of a few degrees, the cold spot stands out, while most of the other areas become blurry with small changes. This strange event became known in writing thanks to that quality pop. Needlets are a modern, multi-resolution cousin. Built as band-limited, quasi-exponentially localized functions on the sphere, they offer two pragmatic advantages over classical wavelets. First, their coefficients at different scales are close to uncorrelated for an isotropic Gaussian field. That makes it cleaner to evaluate significance across scales without double counting the same sky modes. Second, their localization in both harmonic and pixel space helps deal with masks. You can avoid leaking galactic residuals or point source holes into large swathes of the map by discarding needlet pixels whose support overlaps masked regions. When analysts expand the CMB temperature into needlet coefficients and scan for outliers, the Eridanus direction again looks unusual at a certain range of scales, just not as breathtaking once look elsewhere penalties are included. The main idea is easy to understand. An adjusted filter works like a match detector for small features on the degree scale against a background that changes slowly. If the sky is a Gaussian random field, the filtered values should follow a well-known pattern. The CMB power spectrum, the beam, the noise, and the mask should determine how different the values are. It is said to be anomalous if one patch gives a value that is several standard deviations below the mean at a certain size. When you face the facts of finding, things get tricky. After the fact, you know which scale and center make the story the strongest. If you don't give models the same search freedom, letting them also scan over centers and filter radii. The sigma you used is too high when talking about how shocking the cold spot is. Morphology is what makes wavelets different from other things in physics. A real undercompensated supervoid should show a filtered profile with a cold bowl in the middle and, based on the ridge, a gentle, hot shoulder at a radius that is connected to the compensation scale of the void. The net center depth goes down and the hot ring gets sharper with a highly compensated void. The underlying field unwinding gives a cosmic texture template its own pretty fixed radial form. It can also look like a cold core and a shoulder around it, but the relative amplitudes and the way the angular scale changes across filters are different from the void case. To be extra careful, teams don't just say, "It looks cold." Instead, they measure the full radial profile of the filtered signal and compare it to forward models made from a rebuilt Eridanus density field, void, or the texture template family, with the centering set ahead of time. A related tool is compensated aperture photometry, effectively a top hat minus an annulus. It is cruder than wavelets, but useful because its response is easy to compute for a given mass profile. Applied to the cold spot, it gives numbers close to the wavelet coefficients at matched radii, and it makes the ring core trade-off especially transparent. Move the annulus so it overlaps a compensating ridge, and your coldness shrinks. That dependence means you cannot cherry-pick an aperture after inspecting the map. You must lock the radius choices and then test whether the measured annular sequence matches the prediction from the void or texture you claim to see. Needlets help tame masks and beams that make things messy. When the sky is covered, reading off and reducing an amplitude close to a hole makes the result more likely to be positive in terms of variance and sometimes mean. This problem is lessened by needlet pipelines, which either get rid of coefficients whose support crosses the mask or fill in holes with limited Gaussian fields before filtering. Both decisions must be reflected in the Monte Carlo group that makes the point. Low L modes are also linked to degree scales by beams and scanning methods. End-to-end models that run time streams through the mapmaker and component separation pipeline are the only real way to prove that an Eridanus-like depression is not a normal flaw in the system. Crossfield consistency strengthens or breaks the case. If a reconstructed Eridanus density template predicts a specific wavelet radial profile, then the same template predicts weak lensing convergence kappa and an ISW temperature pattern in ordinary, unfiltered space. You can test all three jointly by building a matched filter for each field from the same underlying three-dimensional profile. A win looks like this. The needlet or wavelet amplitudes at adjacent scales line up with the predicted curve. Kappa shows a small co-spatial dip with the expected width, and the unfiltered temperature profile projected from the template matches the observed cold spot once you marginalize over primary CMB variance. A loss is easy to diagnose too. The filtered temperature prefers a ring-to-core ratio that only a strongly compensated void would give, while kappa stays flat, and the tomographic galaxy map insists on compensation too strong to allow a large net ISW. Polarization is the icing on the cake in wavelet space. You can use the same filter on E-mode maps to look for the phase-correlated pattern that goes with the temperature drop on the primordial degree scale. There shouldn't be any noise in the filtered E character for a late-time printing. When you do this locally around Eridanus with pure E estimators and calibrate significance with rotated patches, you get a yes-no answer that is not affected by small changes in the temperature filter. Next-gen surveys, Euclid, Rubin, SPH, EREX, SKA. For the Eridanus problem to be solved, it needs density, space, forms, gas, and a strong way to connect all of these things. That's exactly what the next round of polls will show. Go with Euclid first. He is broad, based on space, and stable. Its near-IR imaging and slitless spectra create a very clean outline of the cosmic web out to redshifts of 1 and above. There are two things that make Euclid strong in the Eridanus cone. First, shapefiles that are much richer than the ones we have now would let you measure a weak negative shear signal on a degree scale from a long trough if it exists. The second thing is that there are hundreds of thousands of safe H-alpha redshifts in the same sky. These redshifts cut the tomographic blur of photometric bins into sharp pieces. There is a single monster tunnel that goes through Eridanus. Euclid was able to follow its spine, piece by piece, in a way that modern mixed photo Z maps can't. Rubin Observatory's legacy survey of space and time adds the depth and colour leverage that void cartography loves. Over 10 years, Rubin's exquisite imaging in 6 optical bands populates the cone with faint galaxies that were previously missing, tightening the bias model that converts counts to mass, and stabilising photometric redshifts with better SED fits and clustering redshift calibration. Crucially, Rubin's billion galaxy shape catalogue pushes void weak lensing from maybe to testable. Even a few times 10 to the -3 tangential shear dip, barely a rumour today, becomes a measurable profile when averaged over the solid angle Eridanus covers. That shear curve, centred and binned exactly as the density map dictates, is the gravity auditor that either confirms a real mass deficit or exposes a tracer illusion. Spherex enters from a different angle, low resolution, all sky near IR spectra. While individual redshifts are modest in precision, the uniform coverage and spectral anchoring/catastrophic photo Z outliers and smooth the selection function across the entire cone. In practice, that means the sausage elongation caused by photo Z scatter becomes quantifiable rather than guessed. With Spherex anchoring the global NZ in Eridanus and Euclid/Rubin providing depth and shapes, the line of sight continuity test, one monster or many, stops being a debate over priors and becomes a measurement with propagated uncertainties. Where stars form and gas hides, the square kilometre array and its precursors take over. Meerkat and ASCAP are already mapping neutral hydrogen. SKA Phase 1 will industrialise both discrete HI galaxy detections at low redshift and intensity mapping tomography to higher redshift. Along the Eridanus path, intensity mapping asks a blunt question the optical counts can't answer alone. Is the mean HI brightness temperature depressed across consecutive distance slices in the same cone? If yes, after brutal foreground cleaning and cross-correlation with optical tracers, the mass deficit story gains a neutral gas corroboration that is insensitive to quiescent/active galaxy mix. If no, if HI stays ordinary while optical counts thin, the void is at least partly ecological, and any predicted CMB imprint must be dialed down by a corrected bias. Experiments on the CMB keep going. The lensing convergence map is already more detailed thanks to ACT and SPT. Simon's Observatory and CMB-S4 will lower the key noise and clean up the large angle polarization. And for Eridanus, this means that template match fits to kappa, made straight from the observed 3D density, will finally have enough signal to noise to be important over apertures of several degrees. On the temperature side, lower noise E-mode maps look at the primordial versus late time turn in the road. A real last scattering dip must have the right local E pattern, but an ISW depression caused by a void shouldn't. All these instruments solve only half the problem unless the analysis is pre-registered and joint. The winning playbook looks like this. Fix the Eridanus cone, masks, centering and tomographic bins before the deepest data arrive. Set a void profile family with priors informed by simulations, central depth, scale radius, compensation, but no a posteriori tuning. Define matched filters for 4 fields derived from the same 3D profile, galaxy density, galaxy shear, CMB kappa, and ISW temperature, and lock the null rotation ensemble used to calibrate significance. Then run the joint fit once the surveys deliver, reporting not just single probe p-values, but the full posterior over profile parameters and the Bayes factors between lambda CDM plus noise, lambda CDM plus this void, and texture-like template. With Euclid and Rubin, miscentering becomes a nuisance you can marginalize, not a guess. With Spherix, photo Z-tails stop inflating elongation. With SKA, gas confirms or contradicts the mass map. With CMBS4, kappa and polarization arbitrate gravity's imprint. There are two clear events that can happen. In the first, Euclid/Rubin tomography shows a smooth, undercompensated, elongated trough with weak lensing and kappa dips that line up. SKA shows a slight HI depression and a faint ridge, and an ISW fit that matches the template gives an amplitude that is about right for a fraction of the cold spot depth. That clears up the math. Late-time gravity adds a measured amount of the chill, and the rest comes from main CMB variation. In the second, tomography breaks the tunnel into small pieces. Shear and kappa stay flat with small mistakes. HI looks fine, and polarization won't show the temperature drop. Then the supervoid theory falls apart, and the case changes to either a rare primordial fluctuation or a template that looks like texture and stays the same even after full sky counts. Bianchi anisotropy templates. One group of big picture theories for strange things seen from a wide angle, like the cold spot, says that the expansion of the universe is not exactly even across all directions. In Bianchi cosmologies, especially type 7H, a small amount of shear and vorticity creates a spiral-like pattern of temperatures across the CMB. This pattern is a broad, slowly curved cold-hot motif with a unique handedness and scale. Early fits from the WMAP era showed that taking away a best-fit Bianchi 7H template could make a number of strange things, like the cold spot, look less interesting. That option is both interesting and dangerous. It's interesting because a single, physically driven template could organize many quirks, but it's also dangerous because the rules that make the sky look neat often clash with rules from the rest of cosmology. What exactly does a Bianchi template predict near Eridanus? Not a compact round crater, but a segment of a global swirl whose cold arc might pass near the cold spot coordinates, with neighbouring warm arcs offset by tens of degrees. If the cold spot is partly a projection of that swirl, then a Bianchi-corrected temperature map should mute its contrast without introducing new artifacts. Crucially, the fit cannot be a bespoke patch repair. The same global Bianchi parameters, curvature, shear amplitude, vorticity scale, must be applied to the entire sky, with the cold spot simply one place where the pattern happens to bite. Right away, two obstacles show up. Firstly, let's look at how well the Bianchi templates match the lambda CDM parameters. In the past, they have liked open curves and shear values that don't match the high-precision acoustic peak fits in the CMB power spectrum or the baryon acoustic oscillation distances. To bring them together, you need a lot of previous stress or non-standard parameter sets that solve one problem by making others worse. Secondly, polarization. There is a very clear large angle polarization signal that goes along with the temperature spiral. Studies from the Planck era showed that Bianchi parameter choices that greatly reduce temperature errors usually predict polarization patterns that are not seen in the data. This means that the simplest versions of the model can't work. Despite those strikes, Bianchi templates remain a valuable null test for Eridanus. The discipline program fixes a compact parameter prior drawn from full sky fits and external geometry constraints, then computes a maximum likelihood Bianchi pattern and subtracts it from multiple independently cleaned CMB temperature maps. With those Bianchi subtracted maps in hand, you rerun the entire cold spot pipeline. Wavelet/needlet filtering at the predefined scale, compensated aperture photometry, local T-E correlation, and match filter tests for the Eridanus void template. If the cold spot's filtered amplitude drops only modestly, and its morphology still aligns with a localized underdensity, you learn that global anisotropy cannot be the main driver. If, however, the cold spot largely evaporates in Bianchi subtracted maps, and the same subtraction leaves other sky regions statistically ordinary, the case for a global imprint strengthens, provided the adopted Bianchi parameters still survive polarization and distance ladder checks. When interpreting, you need to set limits. Because template subtraction is a powerful process, every improvement that seems to be happening must be checked against a Monte Carlo set of uniform lambda CDM skies that have been through the same fit and subtract workflow. If you don't, you might fit the biggest modes too well and solve the cold spot by taking away normal cosmic variation. Does the cold spot look prettier? Is not the right question. The right question is, do statistically defined anomaly metrics, penalized for look elsewhere, move into the expected degrees Celsius minus degrees Celsius range more often than they would by chance under this pipeline? Lensing and large-scale structure offer independent arbitration. A true Bianchi imprint is global and gravitationally shallow. It does not predict a co-located negative convergence kappa dip or a coherent galaxy underdensity. Thus, if Eridanus continues to show even a small template-matched kappa deficit and a tomographic trough after Bianchi subtraction, the residual must be local structure, not global anisotropy. Conversely, if Bianchi subtraction erases most of the cold spot while kappa and galaxy counts remain unexceptional, the balance tips toward global physics, or, less glamorously, towards subtle, large-angle systematics that the Bianchi basis happens to soak up. A practical synthesis uses simultaneous templating. Build a joint model that includes I, the Bianchi temperature pattern with priors anchored to full sky fits and polarization. I, an Eridanus void-induced ISW/RS template tied to the measured 3D density with bias and photo-Z uncertainties, and ISI nuisance templates for known foreground residuals and scanning artifacts. Fit all components at once with a pre-registered likelihood, then examine the posterior on each amplitude. If the Bianchi amplitude is driven to 0 while the void template picks up the slack, global anisotropy is not needed. If the void amplitude falls to near 0 and Bianchi absorbs the feature, but at parameter values already excluded by polarization or geometry, then the fix is unphysical. The only persuasive outcome for anisotropy would be a modest, non-zero Bianchi amplitude consistent with polarization limits that simultaneously reduces multiple large-angle tensions and leaves Eridanus quiet without invoking an extreme void. Why does this thread make scientists scared? Because a confirmed Bianchi signature that is consistent with polarization would mean there is a hole in the cosmological principle, which is the idea of isotropy that most parameter judgments are based on. In an uneven background, every distance, growth, and lensing limit would have to be looked at again. The good or bad news is that new data keeps moving the useful Bianchi parameter space into places where the template doesn't have much control over degree scale features, like the cold spot. NVSS radio dip. A lack of radio sources in the NRAO VLA Sky Survey, NVSS, toward Eridanus was one of the first clues that the cold spot was connected to real structure. The test seems simple. Radio-loud active galactic nuclei and star-forming galaxies fill up big halos across a wide range of redshifts. Counting them all inside a fixed cone asks if the large-scale structure along that line of sight is especially thin. There may be a real, long path through underdensity if the counts are lower than what would be expected from Poisson and cosmic variance. This is the shape that a supervoid would need to give the CMB a late-time chill. But radio surveys are full of selection effects, and going from a picture of faint points to a cosmological conclusion takes a lot of care that many first-pass studies didn't think about. The first job is to reconstruct a spatially uniform completeness function. NVSS was built from many snapshots with changing system temperature, UV coverage, and sky noise. The effective flux limit varies with declination, and subtle beam and cleaning artifacts create stripes. That means you cannot simply cut at a single catalogue flux and call the sky homogeneous. A robust approach estimates the local completeness as a function of flux by injecting artificial sources into the time-ordered data or image plane in representative fields, recovering them with the same pipeline, and then mapping the recovery fraction across the sky. Only after weighting each real source by the inverse of that local completeness and trimming to the shallowest common depth across Eridanus and control cones do source counts become comparable. Next comes masking and flux calibration. Bright sources produce side lobes that, if not properly cleaned, create no-go zones. Those zones differ in shape and frequency across the sky. In addition, modest flux scale drifts with hour angle or declination can push sources across the detection threshold, modulating counts at the few percent level, the exact scale of the claimed deficit. Cross-calibration against independent surveys such as SUMSS in the south or TGSS at low frequencies helps identify and correct these drifts, but only after building a cross-match that accounts for different resolutions and spectral indices. After those steps, one must repeat the cone analysis under multiple plausible flux cuts, beam convolution choices, and mask apidizations to see which features persist. The question about statistics is also very specific. When comparing counts, don't use a simple mean. Instead, use a null that is made up of hundreds of twisted cones that all have the same solid angle, latitude range, mask complexity, and completeness distribution. These rotations take into account the fact that some parts of the sky are harder to see, and they force a look elsewhere adjustment so that you can pick the center and radius of the cone after seeing the cold spot. A deficit that stands out in that small group is the kind of strange thing that needs to be looked at in a cosmic context. A deficit that fades into normalcy once the survey's quirks are taken into account is probably systematic. Even with careful cleaning, interpretation depends on tracer physics. Radio-loud AGN live preferentially in massive, quenched hosts with high bias. Star-forming radio galaxies are less biased. The mix changes with flux limit and frequency, so a uniform flux cut does not guarantee a uniform halo mass selection. If the Eridanus cone happens to include a sky region where radio-loud AGN activity is suppressed by environment in a way that does not track total mass, say, fewer group-scale halos with active jets at a particular redshift slice, counts could dip without a commensurate drop in lensing convergence kappa. That is why cross-checks against mid-IR AGN, WISE color-selected, optical quasars with secure spectroscopic redshifts, and X-ray AGN are essential. A real, integrated mass trough should suppress all of these selections modestly once completeness is controlled, whereas a selection quirk will show wavelength dependence. The strongest use of radio counts is therefore tomographic. Rather than a single integrated tally, one bin sources by estimated redshift using broadband photometric matches or machine-learned radio IR photometric redshifts, and then asks whether the deficit persists across consecutive slices that align with the galaxy-inferred trough. Because radio positions are precise but redshifts are noisy, the power comes from cross-correlation. Measure the angular correlation between radio sources in each slice, and a high-density optical photo Z map in matching slices. A coherent negative cross-correlation localized to the Eridanus cone indicates both traces are seeing the same underdensity. A radio-only dip with weak or absent cross-correlation points to radio-specific systematics or ecology. By introducing enlargement bias, lensing acts as an objective logic check. Large-scale underdensities make background sources a little less bright, pushing some just below a flux limit and lowering counts. This affect's sign and size rely on how steep the radio source counts are close to the flux threshold. If the N/SS dip in Eridanus is really caused by missing mass, some of it should be due to magnification bias with the right sign. You can measure or limit this input by changing the flux cut, which makes it easier to understand the mass and lessens the need to rely on assumed bias factors. What would make a radio assessment convincing? There is a deficit that stays even after completeness weighting, flux scale stabilization, and mask rotation nulls. It shows up in separate southern catalogues with different instruments, but with a smaller amplitude. It stays in radio IR photometric redshift slices that overlap the optical tomographic trough, and it moves with the flux cut as expected. It wouldn't be huge, maybe a few to 10% at most, but it would be strong and able to be repeated. But if the dip becomes less important as you tighten up the systematics, if it changes sign when the flux cut is small, if it's not visible on any separate radio maps, or if it doesn't match up with the optical structure in any way, then there is no longer any radio evidence for an Eridanus supervoid. CIB and SZ residuals. It is said that the cosmic infrared background, CIB, and the thermal Sunyaev-Zeldovich effect are two of the sneakiest fakes in any cold spot study. We are trying to figure out the large-scale structure of both, and they can both leak into CMB-only maps at low levels. Even worse, they mess with degree-scale features at just the right angle. Dusty galaxies that are grouped together create broad CIB changes, and the TSZ from groups and filaments around superclusters can paint faint Y halos near the edges of voids. It's possible for a compensated filter to make it look like there is a ringed hollow when there isn't one. This can happen if leftover CIB or TSZ survives component separation in the Eridanus direction. The CIB is a glow from dusty, star-forming galaxies integrated over cosmic time. Its frequency spectrum rises steeply from 100 to 857 GHz, and its anisotropies are highly correlated with the matter field through halo bias. Modern component separation pipelines downweight high-frequency maps to avoid CIB leakage, but no cleaning is perfect. The telltale of CIB residue is color, a feature whose contrast grows with frequency in CMB temperature units is not the achromatic gravitational imprint we expect from ISW or a texture. A disciplined Eridanus audit therefore repeats the entire wavelet aperture analysis across several independently cleaned CMB maps, and crucially performs the same filters directly on CIB maps reconstructed with aggressive galactic suppression, e.g. GNILC style. If the filtered CIB map shows a hot shoulder where the cold spot annulus appears in temperature, and the amplitude versus frequency trend in the CMB maps mirrors the CIB spectrum, we are looking at leakage rather than late-time gravity. Cross-correlations sharpen the verdict because CIB anisotropies trace the same large-scale structure that lenses the CMB. CIB maps correlate strongly with the CMB lensing convergence kappa. If the Eridanus annulus owes anything to CIB, a template built from the local CIB intensity around the cone should correlate with kappa, but should not correlate with the temperature residuals after you subtract a plausible ISW prediction from the measured 3D density. One practical test, regresses the temperature map within the cone against two fixed templates, the forward-modelled ISW profile and the local CIB intensity profile, then compares the improvement in likelihood. A non-zero CIB coefficient that is stable across frequency splits and declines when the CIB map is phase randomized is a smoking gun for leakage. The TSZ creates frequency-dependent temperature decrements or increments as CMB photons inverse Compton scatter off hot electrons. At 143 GHz and below, TSZ is negative. At 217 GHz, it crosses through zero, and at higher frequencies, it becomes positive. A compensated ring from warm-hot gas on void walls could therefore imprint an annular signal that flips sign with frequency, exactly the sort of behavior achromatic gravitational imprints do not show. Component-separated CMB maps generally attempt to deproject TSZ, but residuals persist at low levels, especially along filaments and near-mass clusters where in-painting is hard. The antidote is to bring the public Y-maps into the loop. Filtering the Compton map with the same wavelet or aperture used on temperature tells you whether a ring of hot electrons coincides with the cold spot annulus. If it does, and if the temperature ring weakens near 217 GHz and strengthens again at higher frequencies with the sign change expected of TSZ, the safest interpretation is SZ leakage is enhancing a ring, not gravity-carved one. Because both CIB and TSZ live in the galaxy web, they can masquerade as physics, precisely where a void model predicts activity. That means null tests must be environmental, not just global. The right control fields are cones matched in galactic latitude, mass complexity, and, this is the subtle part, projected large-scale structure as probed by Kappa and shallow galaxy counts, but which do not host an extreme temperature dip. If similar CIB or Y rings appear at the same rate in those controls, but do not accompany significant temperature craters, then the Eridanus ring is an unlucky overlay rather than a causal explanation. Conversely, if Eridanus is unusually quiet in CIB and Y, yet remains cold in temperature, leakage is unlikely to be the driver. Multi-frequency matched filtering with explicit deprojection is another protection there is. Prepare a 4-part linear model for the temperature patch. The primary CMB realization is unknown, but the covariance is known. The model should include an ISW template connected to the measured 3D density field, a CIB template from the high-frequency map that is smoothed to the CMB beam and apodized, and an TSZ template from the Y map that is mapped to temperature using the known spectral function. You need to find the most likely amplitudes across a number of frequency maps while following the right color law for TSZ and a broad dust SED prior for CIB. The leaking worry goes away if the best fit TSZ and CIB amplitudes are both 0 and the ISW amplitude is not 0. If the opposite is true, ISW is consistent with TSZ/CIB being non-zero but not 0, then the filtered ring is foreground residue and not gravity bookkeeping. If you're not careful, leaks can still lead you astray in 2 ways. The first way is through beam and calibration mismatches. If maps aren't brought to the same resolution with conservative apodization, small changes in the effective beams across frequencies can make color trends that look like CIB or TSZ. The second way is through mask-induced mode coupling. Holes and apodization can mix low-level power into the important degree scales. Full-length models that begin with time-ordered data and fed CIB/TSZ skies and go through the whole process of making maps and separating components are the only honest way to show that your pipeline doesn't create annular features of the observed amplitude when Eridanus is used as a mask. If a small Y ring is real, it means that there is hot gas on the walls that is adjusting. This is a signal that fits in the void model because it makes the compensation tighter and lowers the net ISW. If there is a CIB shoulder, it tells you that dusty stars are forming on those walls, which again fits with compensation that takes away some of the possible hill in the void. In both cases, the gravity trace gets smaller when you look at the foreground. Then the cold spot's answer is less likely to be supervoid alone and more likely to be mostly primary with small late-time garnish, unless lensing degree and tomography both insist on a truly undercompensated tube. Bubble collision signatures. One of the strangest what-ifs that could leave a hole in the microwave sky is one that can be predicted and ruled out. Our inflationary bubble colliding with a partner in a multiverse that is always expanding. A thin, symmetrical disturbance in the primordial curve field moves across a circular area of the last scattering surface in that picture. It adds a disc-shaped temperature change with a gentle ramp and a fairly sharp causal edge. A single bubble collision has geometry, unlike a web of jumbled foregrounds or a lumpy line-of-sight supervoid. It has a preferred great circle axis, a clear center, and a profile family that is controlled by only a few physical parameters: amplitude, angular, radius, and a shape that looks like a linear or tanh-like step when projected on the sky. On degree scales, this can look a lot like the cold spot, central hollow, smooth shoulders, and achromaticity. But it has its own unique signs that an experienced Eridanus program can find. The first and cleanest prediction is polarization morphology. A primordial disk from a collision perturbs the photon-baryon fluid at last scattering, and after projection imprints a co-located E-mode polarization pattern with a characteristic phase. Little signal at the dead center, a rising ring that peaks near the causal boundary of the disk, and a fall-off outside. The amplitude depends on the temperature step, the sound horizon, and the ionization history. But the existence and phase of this ring are robust. That makes the cold spot an excellent test bed. You fix the center from temperature alone, construct the matched E-mode ring template, implied by a bubble profile of a given angular radius, and fit it to multiple, independently clean polarization maps using pure E estimators to avoid mask leakage. A detection of the correct phase E ring that survives rotations and frequency splits argues for a primordial origin. A null, once errors are honest, pushes the bubble idea toward the door. The second prediction concerns large-scale temperature and possibly curvature. A collision imparts not just a local disk, but also a mild, large-angle gradient aligned with the disk's axis. A signature that can bleed into the low L multipoles and, in some model realizations, nudge the spectrum toward a hemispherical modulation. If the cold spot were one lobe of such a pattern, reprojecting the sky along the collision axis should tidy up more than just one patch. Low L alignments become slightly less surprising, and the two-point correlation at very large angles becomes more lambda CDM-like after subtracting a best-fit collision template. This cannot be judged by eye. It needs a pre-registered full-sky Bayesian search for circular disks with a prior on radii and amplitude set by inflationary theory, followed by posterior predictive checks that ask whether the sky looks statistically more ordinary once the fitted template is removed. If it does, and if the required template parameters sit inside the prior volume, the hypothesis survives. If it only works with fine-tuned radii or amplitudes that the theory disfavors, the Occam tax kills the win. A third important test is the lack of late-night mass collaborators. When bubbles hit each other, they change the starting conditions, but not the late integrated gravity field along a certain line of sight. That means there won't be a special co-located decrease in galaxy density once selection effects are taken into account. There also won't be a degree scale drop in CMB lensing convergence kappa, and there won't be any coherent void-like streams in redshift space distortions. You can rule out a texture-like late-time model with polarization and a supervoid with kappa, shear and tomography. Then the fact that there is no LSS parallel is a feature of a bubble, not a bug. On the other hand, even a small template match kappa dip or a continuous underdensity through multiple redshift slices makes the bubble story less strong because it doesn't show a focused late-time matter tunnel. Actions in the foreground help settle disputes. The temperature difference of bubble disks should not decrease at the thermal SZ null, should not increase with the CIB spectrum, and should not be affected by radio source covers other than through variation. Bubble disks are primordial and achromatic. It's not likely that a cold spot is a bubble if its ring changes contrast with frequency after careful beam matching. The bubble's polarization ring is also only E mode up to the first order. Any B mode arc that tracks dust templates points to residuals, not early universe geometry. For the look elsewhere effect, all of these checks must be done with strict consequences. In a busy Gaussian sky, there are a lot of circular circles and centers, radii and amplitudes that scan will always find interesting connections. So, a fair review needs Monte Carlo skies that went through the same search process with the same masks, component separation options, and beam apodization, as well as a joint likelihood that takes temperature and polarization into account. If a disk fits the cold spot, that's not the important question. What matters is how often disks with strong evidence show up in isotropic lambda CDM, and whether the best fit bubble parameters are in the prior box of theory. We have caught late-time gravity red-handed if Eridanus is a real, undercompensated tube. If it isn't, then something even stranger, primordial scars, textures, or a once-in-a-universe fluke, carved a hole in our sky. No matter what, the cold spot is not just a cold spot. It's a test of our whole universe's strength. If you want to know what happened next, go to the next episode. What is the great attractor? And the dark flow? Are they pulling us somewhere? Tap the bell, click subscribe, and then let me know below which theory you think is true today. Because this puzzle gets colder as we look into it more.